do have a Higgs factory, which is shovel ready, as they say, to just begin as soon as the leadership is allowing us. But that still remains, a lot of questions remain, and we want to get to higher energies. LHC has not found new physics in run 2 at the higher energies. We're still exploring deep corners, especially in the electroweak produced new physics. Nevertheless, TeV scale new physics seems a little bit not quite likely to find, perhaps, at least not strongly coupled ones. So the goal is try to see if we can get to the next energy scale. And some of us think that 10 TeV is of interest. I'll say why that is. And it turns out further research is needed in order to build a 10 TeV parton center of mass collider. And that's the reason why there are many options on the table, because each group of people who are good at accelerators are interested in doing something else. But what remains is that the Higgs is a central part of the Standard Model, and it has connections with so many areas. I won't bother even reading all of them, but connects everything. And in particular, percent level Higgs coupling deviations from Standard Model values. In Standard Model, once you know the electroweak scale and once you know the masses of all the particles, including the Higgs, everything is fully specified. And if you have any deviations from the Standard Model values, then BSM physics would be possibly what is affecting it. Now, it turns out if the deviations are at 10% level, which is something that the LHC can do a fairly good job, maybe we can go to 5% level on certain things, but 5 to 10% level points to new physics at about TeV scale, which we have already sort of rolling out. So if we do make Higgs couplings measurement at a 1% level, then that would point to 10 TeV scale new physics, and it would be nice to have options to build 10 TeV scale colliders. So that's the basic motivation for going both for Higgs factory, which would measure the things at percent level, and a 10 TeV machine, so that we can identify whatever new physics which causes potentially deviations at percent level at the Higgs factory. So that's the broad theme in which we were looking at it. So why should I be giving this talk? Well, I'm not an accelerator physicist. I'm not a detector building expert either. And there are way too many collider options for me to be having something to say personally about any of these things. So I just lifted slides from others. I don't have any official leadership position or anything else. I'm just presenting my personal views, although I was part of this NOMAS process. I did work on E+, E-, electron-proton machine at Hera, proton machine at the LHC, and I also happen to have worked on the SLD experiment, which was the only linear collider that we ever built, polarized E+, E- collider. So I think I have some fair idea of what the various advantages and disadvantages of working at these places. So it may be useful to get my view. It's probably unbiased because I worked on all of them, but on the other hand, those are all subject to debate points. I'll be happy to take any questions and we can debate that further. So as I was saying, percent level Higgs couplings is important, and I believe that requires a lepton machine. I think that there is fair degree of consensus worldwide about that. Measuring Higgs coupling, self-couplings, lambda 3, and if you want to do lambda 4, it does require going well beyond HLLHC. We did do careful studies of projections of what the LHC could do with 3 inverse arrow bonds. It barely gets there in the lambda 3 measurement. So self-coupling is a very hard game, and it requires a lot more data. And of course, it requires high energy as well. So going to multi-TeV is needed even to measure Higgs couplings, self-couplings. So that's important. So direct access to TeV scale is of course important for new physics discoveries. If there are any new particles and stuff, as we just talked about, that's something that we want to get at. So one of the, I think that the high energy physics global strategy should be to realize both of these things. So that's where we're starting from. And now I'll sketch what we're starting from. The HLLC is a 27-kilometer machine that we have running, about 14 TeV center of mass. So that corresponds to about 2 TeV in the parton center of mass, let's say, of interest. And we can probably get 200 to 500 inverse femtobarns per year at that machine eventually when we get to the full high luminosity LHC. The ILC is the proposed machine for which we have a design. We just don't have the government go ahead to actually build it. It's a linear collider, which is 31 kilometers in length. It has lower luminosity than HLLHC. Well, of course, it's E plus E minus machine. CERN had earlier worked on a different design. So the ILC is a superconducting RF-based design. The CLIC design, it's also an E plus E minus linear collider, much bigger in size to get to even 3 TeV scale. This one is based on normal connecting RF or maybe even two beam-beam interaction-based machine. So this is a very big, long machine. People have talked about it, but there is a limit to it in the sense that a 50-kilometer footprint is needed to get to 3 TeV. And if you want to get 10 TeV, that's not really likely. So people at CERN and also in China have thought that maybe we should just extend the circular machine, and they're proposing over 100 kilometers. I think that now they're reducing down to about 90 kilometers, but a very, very large machine with center of mass energy in E plus E minus case that they want to start with, they can get close to the top 360 GeV or so. So you can measure the Yukawa coupling to top reasonably well. But they would probably run at 240 for a while. So that's the Higgs factory where you're producing Z and the Higgs. So that machine is very well studied. And going beyond that, once we have something on the order of 20 Tesla magnets, we can have a PP machine in the same 100-kilometer approximately ring, and that would get you to 100 TeV in the center of mass of the protons. So that's about 15 TeV or so in the center of mass of the partons that we're looking at. And these machines have a lot of luminosity per year that you need to get, and that's where we are. So tens of inverse attobonds of data is what they would be collecting. So these are the options that were on the block, and we have recently come up with another concept in the United States that I will say a few words about later in a couple of slides. This is a E plus E minus machine called Cool Copper Collider. I'll talk about that. This is a linear collider as well. It's based on normal conducting RF technology, and it's only 7 kilometers in length. And there are some advantages to that, so that's why I will say I have a couple of slides about that. And that's pretty much like the first two runs of the ILC at 250 and 500 GeV. The center of mass 550 is what C-Cube is thinking of. And then there are several muon collider options which were considered in the past, but we're focusing now on about 10 TeV muon collider machine with about 10 inverse attobonds accumulated in a 10-year period. So that's about an attobond per year kind of accumulation rate that we're thinking of. And this would be an interesting collider as well. So I'll say a little bit more at length. Previously, we were talking about a muon collider. They were talking about, let me say, I was not paying too much attention to it, but a muon collider at the 125 GeV sitting on top of the Higgs pole. It's not much of a pole because the coupling to the muons is very small, so it's just a teeny blip. But anyway, the luminosity is a big problem there, as you can see. It's only an inverse femtobond per year or something like that. So That doesn't seem like a very interesting idea, but muon colliders for 10 TeV seem like a very good option to explore. So that's the landscape that's being considered. I hope I'm still audible. Keep going, assuming so. If there's a problem, I hope you would have let me know by now. So for the circular colliders, E plus E minus colliders, we're limited in energy. The max energy that's considered for a 100-kilometer ring is coming down to about the TT bar threshold there. But a circular machine, its luminosity is high even as you go lower in the root S. So you can actually produce a very large number of Z bosons, tera Z if you like, and of course millions of Higgs, this very, very high luminosity machine. And it has a tremendous advantage in that the 100-kilometer ring would be very useful if you have the high field magnets to get to 100 TeV center of mass proton machines. So both places in CERN and in China propose that they follow the E plus E minus machine with a PP machine going to 100 TeV and producing tens of out-of-bounds of data. The linear colliders, on the other hand, are E plus E minus machines, and the electrons for sure can be polarized and to 80% level or so. That's what we managed to do at the SLC some years ago. These are higher, there's work to be done to get a polarized source with sufficient intensity and all of that. Nevertheless, electron polarization is probably not an issue. Positron polarization is also possible at much lower level. I'm not sure it is needed or not, so that's a debate that the E plus E minus community have had for a while in the ILC context. It has an advantage of energy reach that you can get to higher energies. Here are the machines that were considered in the SNOWMAS report that we were looking at. The lowest energy machines are the 250 GeV Higgs factories, either ILC or CQ. Slightly higher option was picked by the CLIC machine for at CERN. And you could easily think that they can extend out to 3 TeV in a reasonable footprint of on the order of 50 kilometers that we talked about before. Then there are other options that people have considered going beyond the 550 GeV to 3 TeV. That's very expensive because you need to extend the length there. Well, even more advanced technologies are needed if you want to get to 15 TeV, like Wakefield-based accelerators, plasma or laser Wakefield accelerators. And I'll say a few more words about those later. The muon collider is the new kid on the block, if you like, having been revived to about 10 TeV, 10 inverse Autobahn machine. A new international muon collider collaboration has formed and is welcoming participants from all over the world. That's something that people in India should probably also consider. We'll see how these things develop. So as Higgs factories, this is a very busy table. A lot of things were done to summarize the different proposals submitted to the SNOWMAS process by standardizing on this, and various criteria were used to organize them in this table. In particular, it's kind of hard to figure out in very detail how much time is needed for R&D, how long it'll take to get to first physics and all of that. They have done a careful job looking at the components of the accelerators and various other support things that are needed, damping rings, whatever have you, and figured out how much of R&D is needed in terms of time and cost, how long it is likely to take to get to the first physics, and they also estimated how much electrical power, which is a major thing in the sense that you might have built the thing, but if it is consuming huge amount of power over a period of time, it'll cost a whole lot more. So they looked at all of these things and figured out for each of these machines what it would be that it would cost. Those are tabulated here. As you can see, some machines can be done sooner than later. There are others which are extremely attractive from certain parameters point of view, but if you have to wait for 25 years to do the Higgs factory, it's a bit of a problem because we also want to get to the 10 TeV scale. If you don't even establish the scale ahead of time, that would not be particularly good. So in this context, it looks like the winners, if you like, are the circular machines, the 100-kilometer machines, although they have a larger price tag than the linear colliders. If you look at the time scales, ILC with its technical design report ready and costs understood and not as high as FCC EE, if you like, and the power consumption being not particularly bad, it looks like the winning option, except that somebody has to decide to build it. And it turns out the C-cube option that I was just referring to a few minutes ago it does require a little bit more R&D because we need to prepare a conceptual design report. We're not even there yet. So it does take a few years of development. So that would delay the project start to some extent. But once it starts, though, it is actually comparable very much to the ILC. So that's something that some of us got interested in. Now, if you go to the energy frontier machines, the muon collider is the first line here, as you can see. So we focus on a 10 TeV machine. This, of course, requires a lot more R&D. So the R&D we're talking about is over 10 years of R&D, and the first physics will be 25 years or so from now. The cost estimates are quite uncertain. 12 to 18 billion dollars is what we expected the cost would be for a muon collider of 10 TeV. But it has a significant advantage from the point of view of electrical power consumption, which is a very big deal, particularly in Europe. With the cost of energy getting higher and higher, they're paying a lot of attention to how much it costs to operate these machines. Now, I did say about laser-driven or plasma-driven Wakefield accelerators earlier. These are very, very high gradient, GeV per meter and higher. So they don't have a very large footprint for GeV. So you can get to very, very high energies, at least for the electrons. It's still not proven that you can accelerate positrons in these type of accelerators, but some people think that it is feasible. The power consumption is all over the place for those. So for the moment, given all the uncertainties and everything involved, many of us thought that the E plus E minus at 15 TeV and beyond is probably less likely to be available in a reasonable time scale. So that's one thing. Although we in the United States have put most effort in this advanced accelerator program, it does look like muon collider is more likely to go ahead, and Europe, in fact, has begun already investing in the muon collider. But it turns out the proton-proton is the option out there, which is most likely to be realized without all that much R&D. Other than building the 20 Tesla magnets, most of the rest of the thing are very well understood, beam dynamics or scaling the size of everything is very well understood, going from LHC to FCC, similarly SPPS in China. So that part is very well understood. They are expensive machines, very expensive machines. So that's one of the problems that we have to, and also they're a long time scale to get there. So we did a lot of comparisons of power-related things. Luminosity versus energy is what is shown here. And you'll see that in the Higgs factory range, which is shown on the left-hand side, you have all these accelerators which can produce very large luminosity. If you take the linear accelerators and recycle the high energy, either the electrons themselves, electrons and positrons themselves, or recover the energy from them and reuse it, or put them in circular configuration, you get very high luminosity, but people haven't figured out how to actually design something, so they have a long time scale to go. So the winning entries are definitely FCCE and CPC, which are expensive, or the shovel-ready option, which is the ILC, if somebody decides to pay for it, that's the thing that we would definitely want to do. And then we talked about this cool copper collider, which I'll say a few more words about it. In the higher energy for the lepton colliders, the muon collider clearly wins in many respects. You do see the Wakefield accelerators here, but the muon colliders have this advantage that as you go to higher energy, you can realize higher luminosity coming out of it. And it turns out that not only do you get higher luminosity coming out of it, in here it is the purple lines here, the uncertainty on the Wakefield accelerators is very large. So if you want to build a muon collider, if you want to build a lepton collider to get to 10 TeV, the muon collider seems to be the best path to go ahead. For the lower energy machines, for the Higgs factories, circular machines have higher luminosity. The linear machines can go to higher energy. And we try to look at what's the best option to go forward in that. I'll skip some slides, but this one just repeats the point that the ILC and the circular Higgs factories are the closest to getting us physics, and those are the things that we want to pick for Higgs factories to be built as soon as possible. But if you want to go to 10 TeV scale, E plus A minus seems to need a whole lot more R&D than mu plus mu minus or PP for sure. So Higgs factory timelines, on the other hand, are complicated. Now, what's plotted on the table at the bottom here is comparing FCCE to the linear colliders, which are at the bottom. The top two are circular, bottom two are linear. You can see that the linear colliders, you can get to higher energies, but the lower luminosity. So you can get a lot more data very quickly with the circular machines, but you can't get to high enough energy. You can max as M top here. Whereas for the ILC, you can go to 500 GeV, but it will take a little bit longer to accumulate data. So that's what this wording here says. ILC is ready to go. It's just awaiting funding decision. It certainly has the early start, but FCCE and CLIC have TDRs, but they have a constraint that they have to start after the HLLHC is done in a few years. That puts the start point, T0 will be much higher for them. So on this scale, they look like they're a winner, but if the T0 is here, then if starting later, that's a problem. So this is the reason why we were trying to see if the ILC doesn't go forward, are there other ways we can realize a linear E plus E minus machine? And C-cube, the cool copper collider, seems like an interesting idea. So I'll say a couple of words about that in the next two slides. Let's see how I'm doing on time. Sorry, a few minutes late, so hopefully it's okay. Tell me if I'm overrunning here. I can summarize quicker. So what we found is this new option that if you power, this is basically a copper structure of a LINAC that we're showing here. And in that structure, you have these little cavities. And traditionally in the old LINACs, like at the SLC, we were powering all of these things in about a meter-long structure with one RF source. But this idea of a distributed power delivery to these cavities has taken hold, and this is possible because of new machining techniques and things like that, which are allowing one to build high precision waveguides to supply RF power to these cavities, and that has tremendously improved the ability of these accelerators to get to 150 MeV per meter or something. And it turns out that if so that's shown here in terms of breakdown related thing. And if it turns out that you can also cool the copper down to 45 Kelvin, so it's not superconducting, it's just cooled by liquid nitrogen. And if you get to 45 Kelvin or so, you can really push the megavolts per meter, so you have very high acceleration gradients. This has been demonstrated in the laboratory. This is a picture from a publication. Here is one such C-cube structure that was built at SLAC, and they have shown This is done with an X band, but the design that we're thinking of is a C band design, but you can get to 150 MeV per meter. That's about 4 times the accelerating gradient of the superconducting RF that the ILC uses. That's the reason why C cube is much smaller in size than the ILC. It turns out that the machine can even be accommodated on site at Fermilab. This is a map of Fermilab, and it turns out this diagonal area is about 7 kilometers long, and it's possible to design C cube to fit within this. It turns out that the beam delivery system, which is basically a copy of what's in the ILC, is longer than the actual LINAC. So this is something that's doable, and the amount of R&D needed seems to be not too high, but it does require demonstration of multiple strings at cool to liquid nitrogen level to go. So we're seeking R&D funds probably at the level of about $100 million to do this C cube thing. Whether it will be going through or not, I have no idea. But going to 550 GeV is possible within the Fermilab site footprint and accumulate 3 to 4 inverse attobonds. That's what I mean. So any of these machines, whether it is ILC or C cube for that matter, or the FCCE, just focus on these two colored shaded columns, and you can see that okay. So you said you can go longer, so I'm just going slowly, but I can go forward quickly. Okay. So I'll just do muon collider in the next 3 minutes. So the ILC at 500 GeV and C cube are very similar, and FCCE, the performance is almost the same, except perhaps in a couple of places, one does better than the other. For instance, in the TT bar, ILC does better than that. So for instance, if you look at the left-hand side plot here, the ILC versus, but because of the energy reach, as you can go to higher energy, if you can go to 550 GeV, you actually reduce the uncertainty on the top Yukawa coupling by a significant amount because the cross-section gets higher there. So the ILC can get to that very nicely. The die-Higgs production, it's very difficult to improve over HLLHC. With a ILC or C cube of 500 GeV, you can get to 20%. You really need to get to multi-TeV scale E plus E minus machines, and you run out of it. And that's the context in which a muon collider or a proton-proton collider is much better. So at this stage, I want to speed up and talk about the next thing, which is the muon collider, and say a few words about it before I conclude. So the advantage here of a muon collider is it's a lepton machine, so you can get to 10 TeV, and maybe you can do that in one scoop and do both of them. So the muon collider is based on, well, first you have to produce the muons, and you need to accelerate them very quickly so that you accelerate them before they decay. So the idea is that you start with protons, put them on a target, let the hadrons decay, and you have the muons, and you need to focus those muons in both X and Y dimensions, the 6D cooling, if you like. And that's a big deal. And people have demonstrated, mice is the name of the experiment, which demonstrate that muon cooling is probably feasible. It hasn't been done fully, so there's still more work to be done there. And then you need to accelerate the muons, and you want to accelerate them fast, and you have a bigger ring for actually accelerating them, and then you collide them in the smaller ring. So if you have 10 TeV and a ring of this size, which will fit on Fermilab site or as on the order of a few kilometers ring, 6 kilometers or so ring, you need 20 Tesla magnets to do that. But the time scale for all the R&D for muon cooling and all of these things are long enough that we believe that 20 Tesla magnet, which is a common thing with the proton-proton machine, is something that would be feasible. Now, this would be an energy-efficient path with a small footprint, so that's of interest. For instance, the footprint is small enough that, for instance, here is the Fermilab site, and you can fit the muon collider in there. And the 15 TeV accelerator can fit in the 15 TeV proton machine that we have right now. The 27-kilometer LSC tunnel already exists, so you can use that for acceleration, and the new ring that is needed will be much smaller, which will fit inside there. So this 10 to 15 TeV beyond center of mass is equivalent to about 100 TeV in the proton machine. In particular, when you go to technically a vector boson fusion collider, so you produce a lot of Higgses, and you produce the Higgses in W fusion and Z fusion, if you like. And even the di-Higgs production is dominated in the VBF channel, and it's particularly nice to use this channel to make a measurement. And that's the reason why, if you like, the di-Higgs measurement, as you go to higher energies, because of this thing here, as you go to higher energies, this takes over, and you actually start doing very, very well. So if you, even a 10 TeV machine can do better than FCCHH, and a 30 TeV machine will do even better. So I'll skip. There are several cases where you see that the muon collider reach for is higher than LHC by a long shot, and maybe even higher than PP machine, for instance, for some specific objects like this heavy scalar singlet. And one of the important things that people are interested in is to look for dark matter particles in electroweak multiplex. And these are basically, there's no new anything other than a new doublet in which, doublet or even triplet, in which these dark matter particles live. And they interact with normal matter with just the Z or W exchange. And so they're electroweak doublets, right? And it turns out that the thermal target, that's cosmologically viable things, are very, very high dark matter mass is where we want them. And so you need very high energies and a lot of luminosity to get at them. And the various colors here are shown the different center of mass energies of the muon collider. And in the vertical axis are the charge, the multiplets that we pick for various of things. So if you look at the Vino or Higgsino-like thing, a light blue here, which is 14 TeV machine, can easily cover the Higgsino, and a significant fraction of this going to, these are very, very high mass dark matter particles, like, TeVs or 3 TeV particles here that we're talking about. So you have 5 sigma discovery reach for these things if you have a 10 inverse Ida-1 or so luminosity, which is feasible from this. So a lot of these things have been written down. For instance, here is the particle searchers. Here, of course, if you have a colored particles produced, FCC wins over the muon collider. Let's see. I'll skip several slides here, which are about the difficulties of building the muon collider, which we need to address. But I'll summarize them here. So the challenge of building a 10 TeV muon collider is that there is a lot of beam-induced background. The muons decay, and the electrons go and hit all sorts of materials and produce huge showers, and the detector is basically sitting in a bath of huge amount of background, which we call beam-induced background, or BIB. And the detector technology needs to be improved sufficiently so it is radiation tolerant, and also we want to be able to do pattern recognition in that, and also reconstruct jets and so on and so forth. So there's a lot of work to be done there, and maybe design appropriate structures to reduce the amount of background in the detector. The other big problem is that the muons decay and you have neutrinos, and these neutrinos are so intense that the interactions of the neutrinos with matter is on the edge of radiation safety if you don't take any mitigating action. But there are ways you can mitigate the issue by moving the magnets around periodically, or just dithering changing the magnetic fields with higher order corrections to move the beams around to spread the neutrino beam out, so that there is no danger to any humans or equipment which is sitting in the way. And on top of it, there are other questions that need to be demonstrated, in particular the cooling of the muons to produce intense muon beams is not fully understood yet. So there's a lot of R&D to be done. Okay, so what's the path forward? This is a slide that we put together as part of the US NOMAD study. The idea is that if the ILC happens, of course, we have a fixed factory, and then we just decide whether CERN does FCCPP or the US does the muon collider, depending on the decision of what the CERN Council decides about the FCC. And if there is no ILC, then C-Cube may be an option, or maybe ILC can be built in US or Europe, or CLIC can be built in Europe. I don't know what's going to happen. If that happens, fine. If that doesn't happen, then we have a choice of building a muon collider in the US or a linear collider in the US, and the other way at CERN. So those are the kinds of choices that people are looking at we can make. So in summary, worldwide, there are many projects proposed, there are long timelines involved. We're really talking about 2040s and beyond for doing much of this physics, long time from now. But we're particularly concerned that the European plan is starting farther out in the back. That's the reason why we spent time evaluating these in a careful way and trying to see if we can speed up things. And so we added these two options to the whole game. And we're proposing that some of these ideas be taken into account and in the process of project prioritization in the United States. And I think that similar things need to be done worldwide. And hopefully we'll build some international machine as a Higgs factory first, and maybe follow it up 10 or 20 years later with a 10 TeV machine. So I'll stop there.
Thanks a lot. Questions, and please identify yourself so that Vishal can read out the questions to the speaker.
I couldn't hear anything, so somebody has to come closer.
Yeah.
Jidara, can you hear me? It's Jim here. I have a question about the muon cooling, and could you elaborate on the plans for how they're going to start demonstrating doing better than mice?
So muon cooling. Well, the mice experiment, I have a slide somewhere here so I can try to find it. There's the mice. Oops. Did I not put that slide in here? Oh, it's in the main talk, which I skipped over. Okay, so these are the results of the mice experiment. What that is that you have basically a beam coming down here, and you have ability to put some materials here. So you can put an empty target, or you can fill it with liquid hydrogen or lithium hydride. And the idea is that as the muons traverse this magnetic field with this material, they're slowing down, and at the same time you're going to focus them. And you can see in these distributions that they show this amplitude, if you like. If it is empty, upstream versus downstream, upstream is shown in red there, and downstream is shown here. And you can see that once you fill it with hydrogen, you can see that that it has got sharper here downstream compared to the upstream. Again, you can see that with lithium hydride also. So the idea is to use some kind of light materials to slow down the muons while you are focusing them in the other dimension. So it provides you a multi-dimensional cooling, and basically you're increasing the particle count. But they've done it with such small intensity beams, so there's a lot more work to be done in muon cooling before you can say that we can actually use this technique to create an intense beam of muons.
Any other question?
I have a question regarding the electron-positron collider and the mu plus mu minus collider. Electron-positron collider has radiations, synchrotron radiations, but muon has, like, it can decay. Also, the energy at which they are being accelerated will also have radiations. So, and also we are annihilating both the leptons in our collider. So how muon collider is better than electron collider? I am not able to understand this.
Okay. So yeah, if you're comparing 10 to 15 TeV E plus E minus machine, yes, the Bremsstrahlung contribution is huge, and as a result, there's a lot of background. Some of it is not even simulated properly yet. However, compared to that, I would think that the beam-induced backgrounds in the muon collider are significantly higher, primarily because you have a huge amount of basically shower particles at lower energies which are going in. I think that I have a picture here of showing the count of the particles, which I skipped over also as well. So there it is, right? The scale on this, I don't know if you can see it, but it's on the order of 10 to the 7 or so particles, neutrons, and similarly, blue is the photons. Very rapidly following, this is the MEV, so there's only few MEV deposited, but there's so many of them going through the detector, and in the inner layers of the vertex detector in particular, it's huge. The photons, of course, will get all the way to the electromagnetic calorimeter, so that's also a problem. The amount of energy deposited is huge. So yeah, I don't think that it's a trivial problem. If you take the current detectors that we know of and put it in a muon collider, they're not going to work. However, the cost of electronics has come down tremendously, and we have figured out how to build these highly segmented detectors, and we have another 10 to 15 years of available R&D time. I think with timing cuts and energy cuts and innovative designs like trackers with two layers which are very close by, we are using that already in CMS for the high luminosity. We will be able to reduce it, and we've made some studies of that in the muon collider context and shown that you can get reasonably good resolution for jets, and also separate the B and C jets and so on and so forth, and fairly good momentum resolution with a reasonably high efficiency for tracking. So it's all based on a very expensive detector with lots of segmentation, timing, a 4D readout, if you like. I don't know if that answered the question, but that's where you go.
Yeah, I think you are saying that you will have better resolutions here. So, and like anything physics-wise, this could be different apart from just like if we apart from this resolution effects, can the physics be different?
Physics-wise, well, electron, muon, I don't think the physics-wise will make a lot of difference unless there is some really flavor-violating thing that you put in some new physics or something like that. But otherwise, if you have 10 TeV plus E minus machine or a 10 TeV mu plus mu minus machine, if given the same luminosity, the kind of physics that we're interested in, electroweak and other things, will be identical. It's just that accelerator technology is dramatically different and the backgrounds are dramatically different.
Thank you.
Thanks a lot. I think we should now move on. Let's thank Sridhar Dasu once again. I've just been told that the last talk of this session, LIGO, is cancelled.
Right.
So the last speaker for today's plenary session is Abhay Deshpande. And Abhay will be talking about science and physics at electron-ion collider. Okay.
Yeah. No problem.
Thanks
Yeah.
a lot.
I'll probably disconnect because I cannot hear anything anyway other than you're talking at the table. So it's late in the evening here anyway. So uh, bye bye. Thank you very much for giving me the opportunity to talk remotely. Uh, I wish I was there. Bye bye.
Okay. Can you hear me? Can you hear me through the microphone or just me? Okay, very good. Okay, thank you. Thanks to the organizers for inviting me. I'm really sorry I couldn't come here earlier to listen to all your talks. I had to finish my final exam before I could start, so this is the best I could do. But still, I'm delighted to come here and talk about the new project that is starting. The last slide that Sridhar showed you the timeline of all the colliders that are being planned in this world, either in Europe or Asia or in the US. And nothing starts before 25 to 30 years. This is an unusual collider. This is a place hopefully many of you will participate. We are actually building it as I speak. It will be ready in 32. This is the one that is being built, so students and postdocs should watch this. So I'll tell you why we are building this. I'll tell you the motivation for this and what physics we will do. It comes from a nuclear physics community. The collider is being built by the US nuclear physics community. However, I strongly believe that nature doesn't distinguish between nuclear and particle physics. If it gives enough energy and enough precision, we can do both physics topics extremely well. So that's the message I'm going to give you through this talk. The title of my talk is Electron-Ion Collider, Science and Status. The outline will be to give you an introduction. I am fully aware that most of you are high-energy physicists here, so you might not have followed this project. So I'll talk about the introduction and recent milestones. I'll review the science of EIC, and that is predominantly coming from high-energy nuclear science. But I will emphasize also connections to the high-energy physics topic that some of you might be following here. And at the end, I will talk about the EIC project, how it is being constructed, the user group activity that has been set up around it, and the path to realization. And being constructed by, as I said, Office of Nuclear Physics in the Department of Energy, probably the only collider that will be built in the next 20 years. Nature does not distinguish between HEP and nuclear physics. As I said, neither should you. So the three main pillars of the science I'm going to summarize on one slide. When you study high-energy physics using proton collisions at the highest energy, one of the things that you need to do is to know with high precision what your probe is. That is the proton. So you're using the proton as a probe. And here I'm telling you that we don't know much about the internal dynamics of the proton. We do not know how C quarks and gluons and their spins distributed in space and momentum inside the nucleon. We don't know that. How do the nucleon properties like the mass and spin emerge from these interactions? And the two important things that I'll be talking about are the proton spin. This is the proton spin. Just about 30 years ago, we thought that it came entirely from the alignment of the quarks inside, because the dominant quarks, the valence quarks, give the properties of their summing the spins of them resulted in the proton spin. Now we know that it is absolutely not the case. About 25% of the proton spin comes from quarks. Over the last 30 years, we have learned that the gluons provide about another 25% of the gluons, of the proton spin. But that means that the 50% of the proton spin comes from somewhere else. There is nothing else in there, so it has to come from the dynamics, the motion of quarks and gluons inside the proton. So we have to figure out what is that motion, because we do want to understand the property of the proton, that is spin half, that we all use in our experimental science. It turns out that we also don't know the mass of the proton that well. What you as high energy physicists call the origin of mass, which is related to the Higgs coupling, that only contributes to the quark mass, which is about 1 to 2% of the total mass of the proton. The remaining mass of the proton comes from quark-gluon interaction, the energy associated with those interactions. So if we don't know what the quarks and gluons are doing in motion, which might be the origin of the mass itself, we still don't quite understand it. Lattice QCD is giving us wonderful pointers as to where this is going. However, experimentally, we have no idea how to understand it in the context. So this is one of the most important things the electron-ion collider wants to do. If I then graduate to look at the simple nucleus or a complex nucleus, interactions in QCD are not quite understood. How does a color-charged quark and a gluon and a colorless jet interact with the nuclear medium? And here's a cartoon of a nucleus. Inside that is a proton, and the proton has these three dominant quarks. And I do a deep inelastic scattering. If I scatter electrons and exchange a high-energy photon or any other gauge boson, electroweak boson, that interacts with these quarks, and this color charge starts moving inside. What are within the nucleus, and how does the quark, the charged particle that is moving through this whole nuclear medium, know when to pick up the anti-color before it leaves the nucleon, and we as experimentally see that as a color-neutral particle, a pion or a kaon or a hadron. How does that color transition from a colored object to a colorless object? If you think about it in the other direction, that's exactly what we call confinement. Yes? We talk about confinement. How does the color get confined? And to do that experimentally, we need to release it. We have to play with it experimentally in both directions. How does the confined hadronic state emerge of these quarks and gluons? How do these quark interactions create the nuclear binding? These are the only forces that are available inside the nucleus, which means that they have to be responsible to keep the nucleus stable. How does that happen? We don't quite understand. Lastly, we know for about 30 years at CERN that the dense nuclear environment affects the quark-gluon distribution. Classic EMC effect, European muon collaboration, they discovered that the parton distributions in nuclei are different than the ones in protons. What was the origin of it has been explored many times, but it's not been explained. We also know from experiments at Hera in the last decade that the gluon distribution is very special. As a function of momentum of the parton, of that of the proton, that is 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 10th, and 1. That's the X Bjorkane, as some people might call it. The gluon distribution keeps on rising. It keeps on rising so fast that it looks like it's going to become infinite. But we know that that cannot be. Number of gluons inside the proton have to be finite eventually because it's a confined system. And because of the interactions, the color contact interactions of gluons to gluons, you can get very large numbers of gluons by gluons splitting into two gluons. These two will split into two more because each gluon has color charge. It has the ability to do that. In the electromagnetic interactions, you don't see that because the photons are charged less. Whereas gluons, because they carry color in QCD, they can split. So this process can go on, and it is expected that the rise that is coming out here is a result of such QCD interactions. But does it keep on going this way? Doesn't confinement do much? Has to happen. Something has to happen. QCD naturally tells us what needs to happen. If you have too many of these gluons, then at some point in the crowded nucleus or a crowded nucleon, there will be the reverse process of called gluon recombination. Because there are so many gluons in the vicinity, like moving into your train, you will bounce with other gluons, people bouncing against each other inside a very crowded train. And then that means that this process of gluon emission, that is the cause of the rise of the gluon distribution, should be balanced by a gluon recombination, which means that at some point, these two processes, if they become equal, the number of gluons will saturate inside the proton or a nucleus. That saturation has never been seen in experimental life. And that's something that we would like to understand. In fact, theorists have been faster than us and calculated the properties of that system in which you have a gluon saturation. And they say that there should be a saturation. A gluonic matter of universal properties might exist. They have given it an exotic name for color glass condensate. You probably can understand why each one of them is given color, because the origin of this is color, QCD color. Glassy condensate. Condensate is because spin one objects, gluons, large number of them, like a solid state object, they come together. And universal, because we expect that this should be happening in all nuclei. We want to understand that object, that gluonic object that is predicted to be formed. And the second thing we want to understand, if it does form, then we need to understand what are the properties. And that's something that the exotic properties that are predicted by the theory, we would like to understand them. So these were the three main pillars that we identified that no other machine would be able to do as cleanly as possible. That's how we promoted the science of this EIC. Those were the three pillars of the science. We presented this the third time after every 5 years. We have, Sridhar in the previous talk was talking about the SNOW mass, which is a decadal long-term planning process in the US. We, in the nuclear science, we also have the same thing. We meet about 5 to 7 years every 5 or 7 years. The third one at the EIC was presented with technology ready, with theoretical ideas very clearly ready. We got the recommendation that said, we recommend as a community that does different things came together and said that the high energy, high luminosity polarized electron ion collider, which will do the science as the highest priority for new facility construction following the completion of FRIB. FRIB is a facility for radioactive isotope beam, which was being constructed at that time. So we had to tell them that we need to finish what we started, but immediately after we finish, we need to go on to the second big project, which is the beginning of this electron ion collider. The FRIB facility construction ended on this year, on May 9th, and they started physics operation. And the Department of Energy, since 2015, has been ready to take over. After the completion, that construction money is now being directed to the electron ion collider and more. Whenever such a large project gets approved by the science community that we promote it, the Department of Energy says, we need to, before we start funding, we need to go to an independent, external, august committee of experts, not just nuclear or particle physicists, but even outside. Biologists, astronomers, cosmologists sit on that committee. And we want to make sure that the science that we promote is approved by that committee, not from just our inside people who say, I like this facility. And that happens through the National Academy of Sciences, Engineering, and Medicine. So we had a committee in 2017 and 18. After 1.5 years of reviews of the science and the feasibilities, the theory as well as experiment, and the accelerator technology that we think is needed, they came up with the recommendation that the science of EIC is compelling, fundamental, and timely. See, that's an external committee. They don't have the power to say construct it. But they have to advise the funding agency that they say these things is compelling, that people not only in nuclear physics, but particle physics, cosmologists, astrophysicists, and medical scientists think that this is going to be useful. So that's what the recommendation was, and that's considered the highest level of recommendation. It was a consensus study. It's called a consensus study report. And they said that the science of the facility should be based on the emergence of spin, origin of spin that I talked to you about, understanding the mass, the origin of mass, and I'll talk to you a little bit more in the next slide, and the physics of the high density gluon. As we had written in the science document and supported by the long range planning document, the luminosity of this machine should be somewhere at about 10 to the 33 to 34 per centimeter square for a second. That's about a factor of 100 to 1,000 larger than Hera, which was the previous collider that was running in Germany from 1990s to 2007 or so. We want to go to about 100 to 1,000 times more luminosity. We want a broad center of mass range. We want to change the center of mass energy of the collider without losing the luminosity. Most colliders are built to run at a certain energy, and the magnets are designed that way. But then, if you change it, then the luminosity goes up because the magnets are not able to focus the beam exactly in the interaction region as they get the input of the beam. So this was not something. RHIC has been built to actually do this very efficiently. So the hadron beam and the nuclear beam at RHIC, we have changed energies very, very widely without losing much luminosity. But you still know that those who work at RHIC know that the cooling of the beam is necessary at low energy. And that was not normal. That was very unusual, had to be discovered, had to be promoted in the last 15 years. Now we have that for the high energy part. We also want to do this for the electron part. So that's something that we are doing now. A broad range of hadron species, because we want to study the nuclear environment by dialing up the nuclear size. So it's the proton inside the helium nucleus or proton inside the uranium nucleus. It has different path lengths to follow, right? One is a very big nucleus, one is a small nucleus. So you hit something, it interacts, but you can actually change it. And you want that experimental tool available because you want to play with it as you study hadronization and confinement. So those are the kind of things that we want to study. And of course, we want to check one detector against one result against the other. It should be a healthy competition. So we want to have up to 2 experimental facilities. And they supported all of that. So now I'm going to talk a little bit about the measurements. So the first thing that comes to mind, how is it going to be different than the previous experiment, previous measurements that have been done? You want to be first convinced that it will do something new. It will explore something new, some new areas. So what I'm plotting here is that x, the momentum fraction of the parton that is being hit, versus the q squared. Q squared is the resolution with which we can change size of the object that I'm going to see inside the nucleus. So I'm going to change that so that could be a variable energy q squared and variable x momentum. These are the past experimental measurements of the spin structure, the proton with polarized protons. So that has been measured so far. And the electron-ion collider will go into regions which have never been explored. You want to see what happens at extremely low x. Remember, the gluon distribution rise at a low x. We want to go in that region and check that. The same thing with nuclei. Same thing plot here. These are the past measurements from fixed target experiments. And what we will do is to go into regions where no measurements ever existed. And since QCD is an unpredictable theory, meaning uncalculable for all, you need to actually make measurements in that region to understand it, and then put it under the umbrella of understanding perturbative or non-perturbative QCD. So you want to make those measurements before you can actually do this confidently. So let me explain what the origin of nucleon spin problem is. So we know that the proton spin is half h bar, and it has to come from the quark spin, from the gluon spin, and there I mean the orientations of the quarks and gluons towards or against the proton spin. That's I didn't show you there. They're right here. That's the quark spin aligned in ways. But then I have told you that already that about 25%, with high precision, about 3% precision, we know now that the quark spin comes from about 25%. It's with high precision over the last 30 years. We have now also measured at RHIC. Gluon spin comes to about 25%. However, the uncertainty on that is much larger, about 12%. So that's not good enough. But we want to make a precise measurement. So I see, what is it that is the EIC will do? So here is the plot of the G1. You are aware of the F2 structure function. Everyone knows the unpolarized parton distribution function. There is a spin-related one, which is dependent on the gluon's precise measurement, and that is shown here with the uncertainties that come from the current measurement. As you can see, they go all over, and so the red line that is shown here, uncertainties of the gluon distribution are incorporated in that line if we can make a measurement with the electron-ion collider. So a precise measurement of the quarks and the gluons will come out of this measurement that goes in the region where there is no information in the low X region for the spin part. And then the second part is to understand how the angular momenta and the positions of the quarks are distributed inside the proton. We don't know much about them other than the fact that we know that exist. So that's something that we know to respect the proton not as a one-dimensional object, but a multi-dimensional object with internal dynamics and structure. Transverse motion, the finite size of the proton, must create orbital motion. And it would be wonderful to see if we can make a case, experimental case, that energy associated with the quarks and gluons is also the same that can contribute to the total mass. That would be a wonderful thing. We don't know whether they will see it that way, but that's at least what we would like to see. So now let's see how we can make measurements of this three-dimensional object. Now we call proton a three-dimensional object. So nuclear scientists, low-energy nuclear scientists and atomic physicists always used to talk about a Wigner function. Wigner function tells you about an object which has the, so now we are claiming the proton has it, and the things that we can measure about it are the X, which is the X Bjorkane. BT is the distance of the parton, quark or gluon, approximately sitting from the center of the proton, and KT is its transverse momentum. Those are the things that we can measure directly. So I now want to understand, in those three dimensions, what are the partons distributed like? If you know together the X, the BT, and the KT, you know everything about it. You know the position from the center, you know the transverse momentum, you can get the angular momentum, R cross P. Very simple undergraduate physics ideas, but we want to measure them with high precision as best as we can using an electron beam. So if you integrate, if you ignore the BT distribution, what you get is a transverse momentum distribution. We know how to measure them. We measure them routinely for the last 20 years in target experiments. We will extend this technique in the collider way. So from transverse momentum distribution, we will get the KT. If you go in the other direction, we integrate over the KT and go into the coordinate space, then we get two-dimensional order parameters, this 2D coordinate space distribution. And there, we can measure these things using something called deeply virtual Compton scattering and get to something called the generalized parton distributions, which carry all of this information together. Yeah, its parton distribution is just X distribution. Generalized parton distribution has the position distribution integrated into it. So you want to make measurements of these all together. The momentum and position distributions come up from such things, and then we can possibly get towards the idea of orbital motion of parton inside the proton. And let's see how we can do that. I always say that lattice QCD has been one step ahead of us now been calculating. They are calculating these optics, but we need to make those measurements and make those connections experimentally and make sure that we are all on the same page. So the TMDs, the transverse momentum distribution, are measured in the following way. The electron comes in and scatters with the exchange of photons, and it hits, in this picture, cartoon shows a quark inside the proton going orbitally in that direction. And it's here, while it is moving in that direction, the quark starts moving. As it comes to the edge of the proton, because of color confinement, it knows how to pick, we don't understand, but the quark knows how to pick an anti-quark to form a pion that comes out. If it is a U quark that is coming out, most likely it will become an U bar quark from the sea of quarks inside, and that's why you get a pi plus. So if it is moving that way, you get a left, predominantly left-going pi plus. We have seen that in experiments. Predominantly right-going pi minuses have been seen. That means that the d u bar formulation is moving in the other direction. Why? We don't quite understand, but we have seen this in experiments. So if we do that, and if our measurements from the fixed target experiments are still correct, then in the EIC, you will get pictures of momentum distributions which are not symmetric as normally would expect, but these asymmetric in the transverse direction. So you see that the U quark is not centered in the Kx in the center. In Ky, of course, it is, but in the D quark, it is moving in the other direction constantly. Yeah. So those are the kind of things we expect to see in the future. These are simulations based on our very basic minimal model, or not model, but information that is experimentally there. Just enhanced it with high luminosity and the conditions of the EIC. Similarly, something called deeply virtual Compton scattering, where we study EP goes to E prime, P prime, and photon. And the idea behind this is you have a proton, there's a quarks and gluon inside it. You're going to play with the position. You want to study the position distribution inside the proton, You don't want to break the proton. Because if you break the proton, you lose all that information. Then you lose everything. Deep inelastic scattering, you hit the proton, you kill it, you break it. You don't have any imprint of the momentum, neither the position. So we need to do better than that. So what do you have to do? You have to bring that photon in, excite a quark inside the proton, and that quark then emits a real photon, which is purely electromagnetic radiation, Compton scattering, but virtual Compton scattering, deeply virtual. You wiggle the quark emits a real photon, the quark sits inside the proton, which means experimentally, you see a proton in the initial state, that the accelerator gives, the electron comes through, that's again accelerator gives, I do the scattering, and in the final state, I see a proton again, a scattered proton, an unhurt proton. I should see a real photon come out, and I should be able to match it with the collision time. So that's why it's called E prime, P prime, and gamma. That's the internal, that's called the deeply virtual Compton scattering. It was discovered at Hera in 2002 or 2003 in the Zeus and H1 experiment. But if we do that, then we know how to deal with that distribution and get the position distribution of that. Similarly, if it is a gluon that gets excited by quark-anti-quark pair, then in the final state, we see vector mesons. So if you see vector meson coming out, so E, P goes to P, vector meson, and electron, that means that you've dealt with a gluon interaction inside the proton. If it is real photon, it is just that. Yeah? So with these two, you can start information about the C-quark distributions and the gluon distributions. And again, this is the unpolarized C-quark distribution is the polarized. These are again simulations based on what we think is happening. We have to measure them more precisely in the future. But that's something that we plan to do. Last but not the least, I told you about this gluon distribution, low X physics with nuclei. One thing I didn't mention so far is that the highest energy we think we can want to use this for the EIC is about 140 GeV of EP scattering. You would say, hey, well, Hera ran at 300 GeV, and we didn't see anything in terms of saturation. Well, we don't want to go to the higher energy frontier. Ideally, you could build a TeV machine, and there are some ideas about that at CERN as well, and that would do a beautiful job. But we don't have that at our hand right now. So what could be the next best thing as an experimentalist? Well, we have the nuclei. Nuclei pack hundreds of protons and neutrons together. Why don't we use the nuclei as a source of high number of gluons? We are asking for a dense gluonic object. We don't necessarily need the highest energy one. Yeah? So that's the trick that we're going to use. We want to go in the low X direction to see if there is a transition from normal matter to this saturated form of matter in a region where Q squared is large enough that perturbative QCD can start giving calculations. It can be Q squared very small, but non-perturbative QCD is much more difficult to handle. So that's something that we want to do. And the way to do that is to get the nucleus, get it to boost it, and then explore with the high energy photons. And the interactions don't happen on a single parton, but collectively or all the partons. It's called coherent scattering over the entire nucleus. And then if you can do that, then there is a natural factor because of the geometry of the nucleus, a to the power 1/3 factor comes in. So the larger the nucleus, the saturation scale becomes larger. And you can go to highest energy, and the x goes into the denominator. So this factor of a to the power 1/3 divided by x increases the gluon density or the saturation scale. And how much does it go? Well, it's wonderful to see that. Here with EP at 300 GeV, the saturation square, this is lambda Q square, lambda QCD, was somewhere around 0.75. Whereas the EIC with the 40 GeV center of mass with the gold nucleus or 90 GeV, you'll see that we go into much larger ranges in this saturation scale. So we can actually try to get there. If nature is kind enough, we will discover something new with a very clean probe. And what would be the kind of signal we will get? We want to go into this region. This is x and q squared again. We want to go into the saturation scale region. The reason what we see is, if we see a dijet, for example, one of the properties that has been predicted by theory of this object, this gluonic object, is that it is extremely dense. Dense meaning what? 50 to 100 times the density, energy density of, let's say, calculation that exists for neutron stars. So if that is the case, you're actually doing a photon black disk experiment, scattering. You should see essentially diffractive pattern, or you should see something like this. When you create a dijet, only one of them, the jets comes in. So in electron proton, you get two jets, dijet opposite things come out. In the electron nucleus, if there is no such effect that happens, you will again see two jets. But if there is something new, then one of the jets is completely quenched, which means that this is so dense that the jet doesn't come out. And I think this is the kind of thing that high energy physicists have done in the past. So that's something that we would like to do. As the increase in the center of mass energy, you would see more and more of this saturation. And that again is a so I want to summarize the science very quickly now. This is the center of mass energy. This is the luminosity of the machine. This is the integrated of luminosity at that instantaneous luminosity in 1 year operation of the 1 year is effective 1 year operation at RIC, about 6 months that we operate. And you can see that the nuclear physics topics, that means saturation studies, the nuclear interactions in the normal nuclei, can be done very quickly as the luminosity is 10 to the 32. When you start looking at the spin flavor structure or the tomography, we start getting into higher and higher luminosity, and this is something that we can do. If the machine reaches higher luminosities, we can do these sciences in 1 year operation. Of course, it will never be 1 year. The detector will take time. It's a 10 to 15 year program that we have planned around it. Now, comes to my idea, my argument, that once you have a machine like this, a collider, and a comprehensive detector, you can now start thinking that you made the case, you got the money, build it. Now build a comprehensive detector that is also used for something else. So we were discussing this in the SNOMAS 2021 process. This is the high energy physics process, yes, long range planning. What can high energy physicists do in this project? They can get involved too. New studies with proton and neutron targets, impact of precise measurement of PDFs at high X and Q squared, which are required to reduce the uncertainties, the systematic uncertainties on the beyond the standard model effects at LHC. This is something that only the EIC can do in the next 20 years. HERA has given you the uncertainty. That has defined your systematics. We can do 10 to 15 times better. When the luminosity of LHC goes up, there is no way to overcome that part of the uncertainty. The only way you can do that is precise, more precise measurements. The EIC can follow that. Precise calculations of alpha S at different centers of mass energy. It's a very potent way to do that. Heavy quarkonia, 100 to 10,000 times more luminous than HERA with polarization. Most of the theory calculations become easier with higher QCD quark masses. You know that from theory. But now we can match it with extremely high precision measurements. Polarized light nuclei, what you can think about that. Physics of the neutrons. Since the last 10 years, we have seen wonderful expansion of science. We have discovered new things at the LHCb, and we are confirming at EIC, at Jefferson Lab now, the 4 quark systems, 5 quark, heavy quark systems that have come in. what is the nature of that? I think there's a new group of people starting to work on that within the EIC. I already mentioned jets that are tremendously important, but then we go to the traditional aspects of parity, charge symmetry, and lepton flavor violation. There are regions of phase space that theory allows us to explore, which cannot be explored by the high energy physics. And there are people who are now working on standard model and beyond precision measurements to get to lepton flavor violation, universality issues. And I think fundamentally I also believe that all QCD needs to be done with complementary probe. So this is additional probe that we are adding to this. So this is the paper that came out. I'm not going to show much. And there, the high energy physics point of view, the idea of what would be the interest group. Yeah, I'm almost there. The interest group will be beyond the standard model, tomography, the jet set is high energy, flavors, small physics. And this is the kind of the center of mass energy and luminosity where the EIC sits with comparison with the other future high energy experimental facilities. All right, now I want to finish that with the last part of the picture of the talk, is to show where we are in terms of the project. So what we want to do is that we have this RIC tunnel at RIC, and we have the nuclear beams, which we call yellow and blue beam. We'll use the yellow beam at RIC to collide with a new accelerator, the red one shown here, in the same tunnel. So we'll inject the electron beam here, put it through here, and get it in, get into the this ion ring, and collide at possibly at two different positions, detector 1, detector 2, location of star detector, and location of the S-Phoenix detector, which is being built currently at this point. The luminosities I mentioned to you are known, and the science that I mentioned to you before in those blobs can be covered by the machine luminosity that has been estimated right now. So this is a plot where the luminosity is shown as a center of mass energy that tells you the science that we want to do will be done by this machine as best as we can now. It is only natural that these are universal questions that I mentioned to you before that no other facility could answer. That means that those questions were fundamental. They couldn't be answered by anything else. And worldwide community was coming to those questions independently from their perspectives. And so it's not a surprise that now the project has grown with 36 countries, 266 institutions, and about 1,400 PhDs. So we haven't counted in that graduate students yet, because we wanted to have stability to show that there are faculty, researchers of seniorities beyond assistant professor or including assistant professors. They are interested to make the case to the DOE that there are stable people, stable in their career, who will be pursuing that. If you add graduate students, the number goes to about 50% more at least at this time. And this is the distribution of that. All of them are planning to work at the EIC. We are talking to the funding agencies in different countries now, including this country here. And you can see the user group, the activity numbers increase. That group came together in the last 2 years to come up with the idea as to what would be the ideal detector that could be built. So this is a concept detector design. This is the yellow report, and that came out in 2 years. This is the length and the breadth of it, and you can see it is published here. The design is shown. I will spend little time, but you can see the asymmetry in the detector. The hadron beam comes from this direction. The electron beam comes from this direction. Large number of showers of hadrons go in the forward direction. We need particle identification. We need momentum distribution. We need identification at low to high momentum. So all of those determine what kind of detector that we want to build. And it's a typical high energy detector with an added issue with precise momentum, but also particle identification. That's something that is new from compared to the high energy, typical high energy detectors. We have lots of Cherenkov counters, time of flights, etc., embedded within the detector. The detector doesn't stop here. This is about 9 meters. I just showed you this detector. The detector continues because I remember I told you that we want to see the scattered proton in the deeply virtual Compton scattering. And that scattering angle is extremely small. In fact, in the first 5 to 9 meters, that scattered proton does not even come out of the original beam of the proton, which means that it has to give, you have to give it a long space. And that then we put Roman pots about 50, 60 meters away, covering interaction region where the proton actually does come out, and that's where we tag it. So for such regions, the detector extends with the accelerator beamline to about 40 meters away, 60 meters away. Similar on the electron side. This is what a typical detector looks like. Now it's called the EPIC, Electron Proton Ion Collider Detector, and this is a three-dimensional rendering of the same thing. If you look at the technologies that we're using, many of you in the high energy physics, in STAR, in Atlas, CMS, you're using those technologies. The R&D that is going on at CERN at Brookhaven, those groups are working together. There is no difference in the RPC. There is no difference in the the size of the basic electronics that needs to be done. The changes come when the number of energies, number of particles that come out. But that can be incorporated as a dynamic range for any detector. The biggest thing is the radiation, which LHC has a lot more challenging things. But going towards those detectors, EIC projects can help. And this has been supported both by the high energy and the nuclear physics community. A management team has been formed under the Brookhaven management with people from Jefferson Lab integrated into it. Jim Yek is the project director. There are the two people on the detector side, two people on the project side, and then people like me are advisors to the project as well as to the detector to keep track that the science does not get derailed as you start realizing the project with the constraints of the funding and the design technology. So that's the whole activity which is now started. The timeline is given here. This is about 2022, right shown here. 23 transition is right there. We are currently at this point here. There is something called critical decision process. We just got about this early in 2021. We got the CD1, which means that we had to do the engineering design. We are readying ourselves for CD2 and CD3, which is coming in about 8 months. And CD3, which is the beginning of physical construction. Physical construction meaning we actually start thinking in the interaction region in the machine. That will start in June of 2025 at the end of the S-Phoenix run and the STAR physics run. So that's when the construction in the beamline starts. Operation of ordering of our parts has started already. And this is the region where we would be finishing about FY31 is the first collision. That's about 7-8 years from now. There will be the first collision. Those collisions will be useful to make the maximum out of the accelerator. And 33, about 10 years from now, would become the full physics operation. And that's where the machine starts delivering physics. We are also thinking about the second detector now, which I believe will come about 3 to 5 years later than the first detector. And that will be operational in the current position of the S-Phoenix design. Currently, we think that the first detector should go to the STAR interaction region. Some of the details of the interaction regions are more amenable. I want to end with the wise words from Altarelli. In one of his talks, he said the standard model would not have been possible without many decades of synergetic and complementary measurements along EP, EE, CP bars scattering around the world. What he meant was all the things that were happening at that time. And I have added this recently, Rick, CBAP, and LHC. And then I claim that it is only natural that this synergy between various probes, various energies, and properties of the beam can continue into the future, developing the nuclear and the particle physics that we know of going forward. That kind of synergetic discussion has already started at CERN even. We already had it at SNOMAS. Now we just started at CERN with the synergies between EIC and LHC. And they're funded through the same detector R&D programs. Summary. So EIC, a high luminosity, high polarized EPA collider, funded by the Department of Energy, will be operational in the 2030s. It will address some of the most important and profound unanswered questions in EIC. There are two hermetic full acceptance or complementary detectors under consideration. The EIC project, as it has been designed or defined, includes the full accelerator and one full detector. So that part is taken care of. Now we have to make the case for the second one, and that's why I said it will take about a few years later. So that will come. The experimental collaborations are now being formed. There's an aggressive timeline. You want to get the first collisions in 2031 is not very easy from any direction. But that's something that we have set ourselves up, and we are moving forward. There is high level of international interest and partners in having detector and accelerator. So if there are people who want to join, this is a very welcome collaboration. And I think for early career scientists in this room in high energy physics as well, you saw that the tools and technologies are identical. Analysis, detectors, philosophies of analysis are all the same. I think there is a large amount of symbiosis that can happen between nuclear and physics and this. And that's it. New directions in science are launched by new tools, much more than new concepts. And there is a new tool that's coming in the next 10 years. So let's get ready. Thank you.
Thanks a lot, Professor Abu Deshpande, for a wonderful, exciting talk. There are questions there.
Yeah, so I just wanted to know, are there any similarities in the physics program of FAIR and IISc?
No.
Or they are completely complementary?
Well, I would say the tools are very complementary. The FAIR program looks at the nuclear phase diagram. If you ask a much deeper question, the tools and technologies are very different. What are we actually studying in a phase diagram? You're trying to understand what happens to a nucleus when it forms the quark-gluon plasma. Is there a triple point? Is there something like that? Then you ask the same question in another way. Is it a property of the vacuum QCD? Things are happening in there. Now that question has direct complementarity to the EIC physics. When we say that there are gluon interactions or gluon excitations, those have to come from QCD vacuum. So at that level, if you can make an equivalent, I don't know that we can make it. You should tell us, theory should tell us, that if there is a complementarity there. Yes, those questions can then be the same. We will be going at a different way. People don't directly see it that way, but I believe that there should be. QCD is finally interactions of quarks and gluons, so there should be a way to connect it. So,
thanks.
Yeah, so I have two questions, one on the physics side and another on the technical side. On the physics side, I mean, following up on Sridhar's talk, I would like to know in a specific example that how EIC will help some of the the important measurement that high luminosity LSC will do, or as the particle physics community are looking at the next generation Higgs factory. I mean, the Higgs factory, FCCE or ILC. So what are the things that can come, I mean, like the way Hera helped Tevatron and LSC thing, is there some particular measurement at high luminosity LSC or FCCE where EIC measurement can help?
Yes. So I can give you leptoquark. Leptoquark, I was part of the Zeus and H1 leptoquark searches. And we can do much better because of the 1,000 times.
No, sorry, I'm sorry to interject. That is a new physics search. I'm talking of the standard, leptoquark there or not there, I don't know. I mean,
yes, you don't know. Yes.
I'm talking of the standard model measurement. Let's say something related to the Higgs, something related to the top quark, something related to the thing.
So we
where
don't
exactly
we cannot produce top quarks because we don't have the energy. But
I'm sorry, I guess maybe we can talk. I'm not saying that you have to produce top quark or Higgs. I'm saying measurement carried out at high luminosity LSC or FCC, but there is something measured at EIC that can fit into the measurement of Higgs.
PDF, all the PDFs that you see are coming from, that you use are coming from Hera. If you take any of the global PDFs right now, NNPDF or whatever, pick your point, and you take the Hera out of that, and you do the fit using your CMS and Atlas and any other, because that's what you're looking for. The largest leverage comes from Hera measurements, the most precise measurements. And I'm telling you that when you increase your go to high luminosity LSC, the studies that we did at SNOMAS, you will see that the limiting factor are those PDFs. Okay.
Okay.
And
so it's a PDF.
Yes, we will be able to make at least 10 times better PDF measurements in the region of 0.001 to 0.15.
Low X1.
And that's where you will get the maximum buck for your effort. Yeah?
So now
and if that's one. Yes.
The last question, sorry.
Yeah.
The PID part that you are showing in the few slides back,
Yes.
I wanted to know that how low in momentum you can go down, and is there any prospect of
Yes.
using the d by dx of the silicon detector, like in the low momentum side? I mean, so what is that you can go down in the
So we can
momentum? And
so currently the plan, the detector plan, we were, in one design we had thought about using a TPC. The TPC would have allowed us to go to about 500 MeV, right? The current plan, the one that is being proposed, does not have a TPC. They took it out. The second detector, we might think about doing it. It depends upon the drivers, the people who want to build the collider. Currently, we think we can go up to about 2 GeV, 1.5 GeV, all the way to 40 GeV. That's the region in which we need it because of the collision momentum and kinematics. So that's something that we want to do. Kaon-pion electron separation. Electron-pion in the reverse direction also has to be very precise. So that's the range that we are aiming for right now. So between 1.5 to GeV, all the way to 40 GeV, 40 to 50 GeV. Beyond that point, our part of the number, yeah, it just goes down. It's not necessary. But 10 GeV is always, really we need that, absolutely. And that's not easy, as you probably know.
Hi, very nice talk. So you said a little bit about the QGP study in like RIC and LSC. So in this machine, is it all this experiment? Is it possible to have some insight, because anyway the colored charge and converting you are getting? Is there a way, or there any plan that we can have the order parameter measurement in phase transition in this EIC program?
So I don't know the detail of the answer to your question because I didn't quite understand. But all I can tell you is that the nucleus comes in when it produces the quark-gluon plasma. The nucleus comes in, it passes through each other, and it's the gluons that connect through first. They zap, and then they create all this wonderful thing called quark-gluon plasma. If you don't know the initial condition, then there is an initial condition uncertainty that goes into anything that you do later.
Yeah.
There we can give you a lot of help, right?
Yeah.
So that's what we are going to measure, very, very
Oh, I see.
precisely. Yeah?
Three very, very quick questions.
Yeah, thank you for the great talk. I wanted to ask you are you aware of any facilities? So you're probing the proton structure to such great depth. Are there any other facilities that you're aware of where the antiproton structure is being probed, perhaps for interesting
Well,
comparisons?
Well, there is a facility called PANDA, which will rely on FAIR. So FAIR, you know, is in sort of very difficult times right now. But they will make measurements. If that happens, then the antiproton will be there. But not with that precision. It's very preliminary because there has not been an antiproton for obvious reasons, a beam to study this. Proton is fortunately stable, so we can study it in the lab. So that's all I can say. The proton and antiproton being different would be wonderful, right? But we don't expect it. We have looked at very precisely the differences at the QCD level between proton and neutron. That we have measured very precisely. We don't see anything. Yes, there are very interesting things that we can do. Absolutely, no question about it.
I think we should move on to
But
the next one.
experimental.
I'd like to ask two short questions. One, here. Hi. What is the kinematic, kinematic range in which you're looking for saturation? Will it be different because you have an EA collider, you have nuclear modifications of your structure functions. So will you be able to disentangle these two?
No, the region where we expect to see the gluons saturation. The saturation is purely coming from gluons.
Yeah,
And
but
if you
that's
look at
also a low X phenomenon, right? The nuclear
quartz
modification.
distributions have died down by that time. There's nothing there.
I see, okay.
Yeah, I mean, you saw the gluon distributions rise. Below 10 to the minus 2, the contribution in the total number of partons of quarks and anti-quarks and C-quarks, everything is less than 3-5%. We're not going to 10 to the minus 4. This is where we will play with the EIC.
And if I may be permitted to ask my second short question about fragmentation functions. You just had one phrase about it, and you have good particle ID, because you do see a lot of deviation
Yes.
from DGLAP at low X in fragmentation
That
functions.
will be,
So
that is, I think it will be one of the best measurements of fragmentation functions
thank you.
in that region. Absolutely, no question about it.
Can you please go back to the slide where you showed the decision process, the 5-year report and the recommendation? I wanted to draw a similarity with the process that we have in India here and wanted to ask you a question regarding that.
Yeah. Go ahead, you can ask.
The process, you said that that this process happens 5-yearly. That's also something which happens here also. It's a 5-yearly process, and similar documents are made here. It was discussed when you were not here in the conference. What struck me, which is completely dissimilar and very different, is that the recommendation says a high energy, high luminosity polarized DIC is the highest priority for the new. Such a prioritization is something the community here is very loath to do.
Yes.
Would you say anything about whether it is?
Okay, thank you. Thank you for that question. So, yes, well, you know, I came from high energy physics. Zeus and H1 was before I did that, SMC, the spin problem. So I was a particle physicist to start with. I came into the nuclear physics community because Rick was a nuclear physics machine. I was doing the same thing. I suddenly became from particle physics to nuclear physics. Now, once you come into this large program, and Dasu talked about previously, the SNOMAS process, that's a decadal plan because their machines are bigger and the costs are bigger. So that's a decadal plan. We have a 5-year plan. And it's not exactly 5 years, 5 to 7. But what we do is every 5 to 7 years we meet and say, did we accomplish what we said we would do in the last 5 years, in the last plan? What went wrong and why did it go wrong? If there was something with the implementation, we fixed it there with the information, with direct communication with the Department of Energy, which is the funding source. But then we have also done a lot of physics during that time. So we all come together and say, hey, this is what we found in this part of science. That is something. Now, nuclear physics is a broad thing. Every nuclear physics in the US studies all forms of matter. That's the idea, all forms of matter, which means that it studies the whole nuclear matter, as we purported there. It studies the hot nuclear matter. It studies neutrinos as well. It's part of the uninteracting matter. It studies the stature, So all of this comes in, and this radioactive isotope, radioactivity, to find out how many elements exist. This is all under the one nuclear umbrella. So it behooves us to come together and say, what are the big things? Not your paper or my paper or just how much was the glue on. That is not what. What did we learn out of that process? What did we learn about nature is the bigger question we ask. Not within the community of high energy QCD, but including the neutrino scientists, including the FRIP scientists. If they discovered a new element, I want to know why is it big? How does it impact the evolution of the universe? Because that's what they are trying to make the case for. So we discuss this, isolate this upper and upper places, and think about it at a much higher level and say, what were the major things that we did? And that means that we can now predict what needs to happen in the next 5 to 7 years. Once you've asked that kind of a question, then we can now talk about not just my private interest, but also the field's interest. And that level of discussion has allowed us to make these kind of statements that said, okay, we can study FRIB, these extra elements, and that's going to happen. That's going to happen anyway now. So what is the next big thing that our students and postdocs and the next generation needs to know? What needs to be ready for them when they are ready to take their leadership in the community? So then we say, okay, then next thing that has to happen is in the other field. So now that's the big picture. In this particular case, what had happened was the neutrinoless double beta decay and the EIC were going head to head. Meaning scientifically we were saying, this is a great thing to do, we have to do it. The neutrinoless double beta decay is a small community. It's a small community, yes? RIC and JLab coming together was a huge thing in nuclear science. So everyone expected that this was going to happen in a way that the double beta decay will not happen. But I firmly believe that double beta decay is a very important experiment. We need to do as human society, we need to do that. And once you accept it because you understand the science at the highest level, you say you cannot kill that experiment just because it is a smaller community. The voice should be heard. And that then became the implementation plan. So how do we do neutrino double beta decay in spite of the fact there is a larger number of people who want to do EIC? And it's okay. If the science is good, we have to support it. So that sentiment comes in, and then there was an asymmetry in the costs of the two projects, this particular one. And they said, this is going to be $1 billion plus, $1.5 billion plus. Neutrino double beta decay was at that.
The scan is completed.
You.
Okay, so be back soon.
Yeah, sure.
It is all guys this time.
So, Anupam, you can start sharing. We can check. Maybe I can start.
Can you see my screen? Can you see my cursor also?
Yeah, I can see both.
Okay, thank you. Yeah.
Yeah, just a second. Yep. I think now you can see my slides and also cursor. Okay. Now is it fine? Okay, thank you.
Yes, yes.
Yes.
Yes,
Yes.
yes, yes, I can.
Hi, Rohini. I can't hear you, unfortunately.
I said, do I spot a sweater actually?
Yeah, you do. You do. But that's because I'm going to put in tonight.
Ah.
So, hello Biswajit, hello Anupam.
Hello.
It's really nice to see the people who have won the award. So all your talks are ready?
Yeah.
Yeah. So we look forward to hearing you.
Thank you.
Thank you.
I just wanted to tell you something that we are requesting Physics News to do an article, and in the article we want to do a summary of a half-page to one-page summary of each person's work. Okay, what is actually in your thesis? So it would be nice if you could do that. Would it be possible? Yeah.
Yeah, it's
okay.
possible.
So we'll be writing to you. So once it is okayed by IP and so on, then we'll get in touch with you. Okay.
Yes, sure.
Yeah. Where are you right now?
Also, I think so.
I am in Lausanne now, in Switzerland.
Okay.
Yeah, I'm in US. Yeah, I'm in US. So I'm currently at Minneapolis. Yeah.
Yeah. So what time is it?
My time is 11:49. So it's close to 12.
Close to midnight.
My time is morning 6:50.
That is the harder one actually. It's the more difficult one.
Where are you, Shubham?
Yeah, so I'm based at Minneapolis, University of Minnesota, but currently I'm at Snow Lab, Canada. So it's almost 1 for me in the night.
Oh, okay. So thanks for coming at this ghastly.
But I guess with you guys, that is, as Nilima says, that is perhaps
always a problem with this
better end of the day than the morning.
Better time than the morning one.
Yeah.
Well, yeah.
Okay, I think now people are filing in slowly, looks like.
You can see what they are doing?
Well, I can see at the background.
Okay, fine. I usually do a little reminiscent of Rahul, which I won't do this time. I'll request Rohini and Devashish to do it. Do you hear me, guys? They can do it.
I hear you, but
yeah.
I think
they can do it whenever Vedang schedules them. Okay.
Well, maybe Rohini would be the best person to do it, and also we are running short of time, so let's just have Rohini talk about him.
No. We'll do it later. I'll just start off in 5 minutes so that we are late. So we'll start as soon as we can. Right?
Okay.
I think we will start after Nilima's remarks, and then if time is left after the presentation, I can say a few words, since I'm suggesting this since you are running a little late.
Yes, I think that will be, that's the idea. Yeah.
No, I'm just saying that in principle, normally we do it after Nilima's remarks, but since we are running a bit short on time, I wouldn't want to take the time of the presentations. So let's do the presentations. Anyway, there are no questions. These presentations don't have really discussion and questions and answers in a big way. They can be something very burning, perhaps. So after that, I can just say a few words about Rahul, and as well as, add to whatever you have said about this year's selection process and my thoughts or take on that also, if necessary. So I will speak at the end.
These poor guys have to sleep.
Not Vishwajit.
Yeah.
Oh, I just came to office in the early morning.
You have excellent Italian coffee to keep you awake. No, you're in Lausanne.
I'm in Lausanne in Switzerland, but also we have a very nice coffee room here in the office. Like, yeah.
I am sure even in Lausanne you get the same excellent Italian coffee. Don't
Yeah,
worry.
that's true.
But you all guys are in cold places.
Yeah.
Well, they're in cold places with good heating. We are in cold places with bad heating.
Yeah, you are in Delhi. Yes, indeed.
Well, no, I'm in Bangalore actually. But
oh, you are in Bangalore. Yes, I forgot. But Bangalore is not that cold.
It was last week.
Yeah, but right now I'm sitting with my door open. I'm actually at home. Not
I've been using it even in Chennai.
So now I just see only Bedanga walking towards the door of the hall. Yeah, but people are coming in, I can see.
Yeah, so tell me when to start, huh, Vedant? Yeah.
स्वेटर घालून येते कारण दार उघडल्यावर छान वाटतंय पण
Not actually an IISER. This is some which.
Sorry? What did you say?
This is not actually an IISER, I heard. We should ask.
Yeah, it doesn't look like. I mean,
I can't remember what IISER looks like.
I mean, I remember IISER this thing hall, but maybe they have changed since I went last.
It could be, or they can be a new room. Who knows? People are coming. Okay.
Trust Beranga to arrange everything that we can see the audience also. It's a big hall.
टॉक वगैरह देनी है तो उसके लिए ना ये ना ये हाँ I'm from IISER. Maybe we should start. Huh? Okay. Okay, we will slowly get started. So welcome everyone to this session on IPA Rahul Basu Best Thesis Award in High Energy Physics. First I will request Professor Nilima Gupte to say a few words. Yeah, Nilima, over to you.
Yes.
Yes.
Okay. There's a little bit of a time lag, so you may find this slightly disorienting, but okay. I have now realized there's a time lag. So welcome everyone to the to the ceremony, to the award ceremony of the Rahul Basu Award, which is administered by IPA, and to this I have to thank IPA for very efficient administration of this award, and I have to also thank Vedant for the very beautiful way in which he has conducted this entire process by which the award has been selected. One thing which I would like to say about this award, we have been giving this award since 2012. And one thing which I would like to say is that this award we are really proud to say this award has always been given to very excellent theses. It's been very impressive to see the level of theses which have appeared in high energy physics. Year after year, this award is now, I think, we've given this 6th time. This is the 6th time. And that each time it is very difficult to decide who the award should go through. So the committee really has a very difficult time deciding. This time was no different. And it was really difficult to decide who are the people who should be getting the award, because the quality of the thesis was so high. So I would really like the speakers who have come, I would really like to request all the HEP students in the audience to see that this is the level at which what is the level they should aspire to, because I think our speakers today can really be role models for the HEP student community. Mr. Basu is my late husband. Usually I say something personal about him, but given the time constraints, I think we'll start off, and I'm handing over the charge of saying something personal about him at the end to Professor Rohini Godbole, who was a really good friend of both of us and still is mine. So let's without further ado, let me hand over to Vedant to start the proceedings. Vedant.
Yeah, thanks, Nilima. Let me share some slides. Okay. Let me say a few slides about IPA and the process that was followed for this award. So IPA stands for Indian Physics Association, which was founded in 1970. And if you want to connect, this is the website, the emails, the YouTube, Facebook, and Twitter links. IPA has 47 chapters, close to 4,400 members. All the chapters are spread all over India. It organizes special lectures, does licensing between national bodies, gives out biennial awards, and also has many international linkages, including American Physical Society and IOP UK. If you want to become a member, there is membership forms available on the website. Also, IPA recently endorsed the global effort on the role of physics in green economy. IPA also comes out with a publication, Physics News. This is the IPA bulletin. You can find details in the link given. There are also two interesting sections, Meet the Physicist and also profiling of physics departments in different institutes. If you want to contribute to that, you can send an email to this, which is given on the bottom of the slide. The present office bearers, President, Vice President, General Secretary, Joint Secretary, and the Treasurer. IP also has a Gender in Physics working group since 2017. It's a platform to address various issues related to gender parity in physics profession. And we have been trying to make it a regular, a special session is being organized in Symposium as ours, also in nuclear physics, to bring more awareness about this area. So now let me come to the brief details about this IPA Rahul Basu Best Thesis Award in High Energy Physics. The two winners will receive a cash prize. Currently it is rupees 25,000 and a citation, and the runners-up will receive citations. The award, which is coordinated through the Indian Physics Association, is given for the two most outstanding PhD theses from India across all areas of high energy physics, including theoretical and experimental, during a 2-year period. It started in 2012, 14, 16, 18, 20, and this year 2022. These are the committee members. And in addition to that, we try to get reports on the thesis. More than 70 colleagues from the community were contacted to get reports, and those were thoroughly discussed by the award committee to come to this conclusions. We received 30 nominations, and we have awarded 2 best theses and 2 honorable mention. At the end of the deliberations, committee placed on record that they congratulate all the candidates who were nominated, and we're very happy to note that several interesting work in the field of high energy physics is being carried out in India. The committee felt that many of the theses received contained high quality work, and the decision making was not at all easy. The committee also deliberated on the gender parity in the selection of best thesis, looked at previous records on this aspect for these awards. The committee also placed on record their sincere gratitude and thanks to several colleagues from outside the committee who assisted in the evaluation process. So with this, let us join in congratulating the Best Thesis Award in High Energy Physics to Dr. Anupam Rai for his PhD thesis, Unraveling the Mystery of Dark Matter with Stars and Black Holes. And the second best thesis out of the 2 is Dr. Subham Pandey for his PhD thesis on performance of high granularity calorimeter prototypes for the CMS high luminosity LHC upgrade in the beam test experiments. For the runners-up or the honorable mention, we have Dr. Biswajit Sahu for his PhD thesis, Classical and Quantum Subleading Soft Theorem in 4 space-time dimensions. And we have Dr. Samir Banik for search for lightly ionizing particles in super CDMS and simulation of neutron backgrounds. So please join me in congratulating so the Indian Physics Association Rahul Basu Memorial Best Thesis Award in High Energy Physics. So this was the brief sort of presentation. Now all the 4 winners and the 2 winners and the runners-up are going to make presentation. We will, let me stop sharing and we will have first Dr. Anupam Ray to make the presentation, and it will be 15 minutes plus 5 minutes.
Okay. Can you see my screen?
Yes.
Okay.
You can proceed. Yeah.
Okay. Thank you for this nice introduction. Thank you everyone for this nice opportunity. I am really glad to share my work with all of you. Today, I will be talking about unraveling the mystery of dark matter with stars and black holes. This is the title of my thesis, and this thesis based on the following works that I listed here. Okay, so let's begin. So we know that dark matter exists, and we know that dark matter is omnipresent in our universe. But we do not know what is dark matter. So that is the question that we thrive in the modern day, that what is dark matter. And one of the major reasons that we do not know that what is dark matter is actually dark matter covers a wide range of masses. So if you look at this schematic diagram, you can see the dark matter minimum mass can be around 10 power minus 20 eV, and the maximum mass can be few solar mass or so. So clearly this mass range spans more than 80 orders of magnitude, and it is gigantic. It's very hard to find this thing in this huge mass range. Of course, I will not talk about this huge mass range. I will talk about 2 particular mass range. So as promised, that I will show you that stars and black holes can actually unravel the mystery of dark matter. And more particularly, I will talk about 2 types of dark matter candidate. The first one I will be talking about, this is primordial black holes as a dark matter candidate. So ultralight primordial black hole as a dark matter candidate, and ultralight means I will talk about primordial black holes of mass 10 power minus 18 solar mass to 10 power minus 16 solar mass. And secondly, I will talk about WIMPs, the weakly interacting massive particles, which are very popular dark matter candidate. And I will talk about WIMPs in the GeV to PeV mass range. So in this diagram, I will focus in this range and this range. Before going to the talk or before going to the presentation, let me state my results first. The two results I will try to convey you. The first result is ultralight primordial black holes. That means primordial black holes in the mass range of 10 power minus 18 solar mass to 10 power minus 16 solar mass. They cannot be a significant fraction of dark matter. In other words, primordial black holes in this mass range cannot form 100% of dark matter. And why? That I will tell you. And the other results I will show you that observations of stars, observations of neutron star will provide stringent exclusion limit on WIMP interaction with ordinary matter. So this is the 2 results that you will take away from this talk. Okay. So now let's proceed a bit more detail. So we know that dark matter are typically searched in 3 ways. One is direct detection. So where what happens, the dark matter scatters with the standard model particle, deposits some energy, and we want to measure this energy. So this is the direct detection scheme. And the other one is indirect detection scheme. So what happens here? The 2 dark matter particles annihilates or dark matter decays and produce standard model particles. And in dark matter dominated region, we want to see these anomalous particles, and if we find them, then we detect dark matter. So this is the sort of indirect detection. And the other part is collider search, where we make dark matter through particle collisions. So there are 3 ways: direct detection, indirect detection, and collider search. If I classify my work in 3 directions, so I will cover direct detection and the indirect detection. So the primordial black holes thing that we will be talking about, this is indirect detection, and the stars thing that I will be talking about, this is roughly astrophysical direct detection. Okay. So let me start to the first half of my talk, unraveling the mystery of dark matter with black holes. Okay, so before going to that, let me give you a brief introduction, and I try to make the slides in a bit non-technical way. If you want to some technical conversation, I am happy to do that. So primordial black holes. Primordial black holes are exotic compact objects. They formed in the early universe, and they are formed possibly by the gravitational collapse of overdense regions. So what happens at very early universe? There are some overdense regions. This overdense region collapses, and these overdense regions form primordial black holes. And what is the mass of this primordial black hole? My primordial black hole has a wide range of masses, and it depends on the time of formation. So if I say that, okay, after Big Bang at t equal to 0, let's say at particular time t, the primordial black hole formation happens, and this time t will determine what is the mass of this primordial black hole. If you again look at this diagram, you can see that if the primordial black hole is produced, let's say at Planck time, which is 10 power minus 43 seconds, its mass can be 10 power minus 38 solar mass. And let's say if it is produced after 1 second after Big Bang, it has a mass of 10 to the power 5 solar mass. So clearly, it spans a wide range of masses. Okay, so these are the primordial black holes. But so people talk about WIMP so much nowadays, but primordial black hole is one of the dark matter candidates that is proposed much before the WIMP. But people are not excited about primordial black holes that much. But after in 2015, LIGO collaboration has detected a merger of black holes, and after that, some proposals came that these black holes might be primordial in nature. So after that, primordial black hole as dark matter has grown some interest in the community. Sorry, there is some noise. Is there any question, Vedant? Oh, sorry.
Actually, please mute the local computer. I think that's what is creating echo.
Okay. Sorry. I thought there is some question because I cannot see the other thing. Okay. Sorry. Okay. So primordial black hole as dark matter was proposed much earlier, but after the detection of gravitational wave in LIGO, people are really excited about primordial black holes as dark matter, and these are the lists that search primordial black holes as dark matter. So you can search via Hawking radiation, you can search via lensing, you can search via gravitational wave, you can search via their accretion, you can search via dynamical effects, etc., etc. But as promised, I will be talking about ultralight primordial black holes, and ultralight primordial black holes are sensitive to Hawking radiation. Since there is not much time to discussion, I will just give you a brief sketch of my results. So what happens? So suppose you have ultralight primordial black holes. That means primordial black hole in the mass range of 10 power minus 18 solar mass to 10 power minus 16 solar mass. You can compute their Hawking temperature. So these primordial black holes Hawking radiate and emits particles. So depending on its Hawking temperature, it can emit photons, it can emit neutrinos, it can emit electrons, it can emit positrons, and other particles. What we did, we searched all these particles in various particle physics detectors. For example, we searched these Hawking radiated neutrino in the Super Kamiokande. We searched these Hawking radiated photons through X-ray telescope. We searched these Hawking radiation electrons and positrons through galactic center gamma ray emission. So we did a comprehensive search of these Hawking radiated particles. Of course, we do not find any. And since we do not find any, we put a stringent limit on primordial black hole as dark matter. So this is the summary of the first half of my talk. So this is the visual summary. I will give you a detailed summary in the later slide. So this is the visual summary. The y-axis of this plot is FPBH. FPBH means dark matter fraction of primordial black holes. FPBH, if FPBH equal to 1, that means primordial black hole forms 100% of dark matter. And if FPBH equal to 10 power minus 1, then that means primordial black hole forms 10% of dark matter. And the x-axis is MPBH, which is the mass of the primordial black hole. And you note that mass of the primordial black hole starts from 10 to the power 15 gram, which is around 10 power minus 18 solar mass. Why is that? Because all the primordial black holes whose mass is less than 10 power 15 gram, they have already evaporated. So they do not exist now, and therefore they cannot be dark matter because they are gone. So we only sensitive to primordial black holes above mass 10 power 15 gram, which is 10 power minus 18 solar mass. So these four lines are the limits that we have derived in our work. So this is the limit, and from this limit you can clearly see that from 10 to the power 15 gram to 10 to the power roughly 17 to 18 gram, primordial black hole cannot form 100% of dark matter because all these shaded regions are excluded. Okay, so this is the main summary. Primordial black hole can actually make up a large or even entire fraction of the dark matter density. I should have mentioned this point in my earlier slide also. So for example, in this plot, you can see there are colorful lines. For example, these are the limits that we derived. There are other limits in the high mass range. But actually there is a mass range here. For example, from 10 to the power 17 gram to 10 to the power 23 gram, there is no limit. So in this range, primordial black hole can form 100% of dark matter. So and that I try to convey. The primordial black hole in certain mass range can form entire fraction of the dark matter. And it's a bit surprising because primordial black hole as dark matter has been proposed in 1970s. So it's been 50 years, but still there is a 6 orders of magnitude where primordial black hole can form 100% of dark matter. Ultralight primordial black hole, which is the interest of my thesis, ultralight primordial black holes emit particles via Hawking radiation. They act as a decaying dark matter. And these Hawking radiated particles can be searched at various detectors. And if you do not see these particles, you can put stringent limit on primordial black hole fraction of dark matter. And lastly, we provide world-leading exclusions on ultralight primordial black hole as dark matter. So this concludes the first half of my talk. Now I will quickly flash on the second half of my talk. I will talk about now WIMPs, and I will talk about how stars can unravel the mystery of dark matter. So so the first half of my talk was how black holes can unravel the mystery of dark matter, more particularly primordial black holes in the ultralight mass. Now I will talk about how observations of stars, more specifically neutron stars, can shed light on WIMP properties. Okay, so before going to that, let me again take a step back. So this slide, the title of the slide is a bit interesting, that going underground or looking at the sky. So we know that in order to search for WIMPs, so weakly interacting massive particles are very popular dark matter candidate, and people are really trying to search the interaction strength of WIMP with the ordinary matter. So people have built various detectors underground which tries to see the recoil signature of WIMP to our baryonic matter. And of course they did not find any, and therefore it puts some constraints on WIMP interaction. So this y-axis of this plot is sigma chi n. Sigma chi n is WIMP interaction strength with us, WIMP interaction strength with nucleon, and this m chi is the mass of the WIMP or mass of the dark matter, and all these shaded regions are excluded. So you can clearly see that WIMP cross section of, let's say, 10 power minus 44 centimeter square or 10 power minus 45 centimeter square is almost excluded. But you also look at this plot, there is a certain feature that if you go to very low mass or if you go to very high mass, the limits are weakening. So this is because if you go to very low mass, the dark matter particle does not deposit sufficient energy, and if you go to high mass, the number of dark matter particles are decreasing. So for these underground detectors, very light dark matter and very heavy dark matter are at the blind spot. But if you rely on your astrophysical observations, then you can show that this very heavy mass and this very light mass can efficiently probe with the astrophysical observations. So that is the basically motivation of the site. For searching dark matter, you can go underground or you can look at the stars. And I will try to show you that looking at the star probably the best way forward. Okay, so to give some more context, so what the actual thing that I am talking about. So the thing that I will be talking about here, that suppose you have a compact star, let's say neutron star, and if you assume that dark matter has non-zero interaction strength with neutron star, dark matter has a non-zero interaction strength with neutron, then what happens? The dark matter particles from the galactic halo will enter the neutron star. It will hit the neutrons in the neutron star, and as a result, they will lose the velocity. So dark matter particles will come from the galactic halo. It will hit the neutrons because the non-zero interaction between dark matter and neutron, and as a result, it will be slowed down. So, and it can so happen that the dark matter particles final velocity after scattering, after single or multiple scattering, the dark matter particle final velocity falls below the escape velocity of the stellar object. Then it will form a bound orbit, and eventually it will be captured. So the dark matter particles will be captured in the neutron star. Now, suppose the dark matter particles are annihilating. Then what happens? These captured dark matter particles will annihilate among themselves inside the neutron star, and eventually you can show that it will cause some extra heating in the neutron star. And you know the neutron star heating measurement. So since you do not observe this excess heating, from there you can put constraints on dark matter parameters. This is the scenario for the annihilating dark matter. But what happens for the non-annihilating dark matter? For non-annihilating dark matter, there is a very interesting phenomenological signature. So non-annihilating dark matter, what happens? Since they are non-annihilating, with time there will be more and more number of dark matter particles. So with time there are accumulation, and accumulation, and after some time there will be so much dark matter particle inside the neutron star, there will be a dark core collapse, and you can show that there will be a micro black hole formation inside the star, and this micro black hole, due to its black hole nature, will consume the star. So therefore what will happen, if you take some values of dark matter mass and cross section, you can show that the stars will not exist, and since you saw the star, therefore it will put some constraints on your dark matter parameter. So this is I already talked about my last slide. So for annihilating dark matter, what will happen? The captured dark matter particle annihilate, it will create an extra heat. For non-annihilating dark matter, there will be more and more accumulation, and eventually there will be a black hole formation which will destroy the star. And since you know the star exists, therefore it will put a bound. So this is one of my plot from our paper. So this is again the same plot, the sigma chi and m chi, and these colorful lines are the lines obtained from the underground detector. So these are the lines from the, if you go to underground. But if you look at the stars, this is roughly the bound we will expect. And as promised, at very low dark matter and very heavy dark matter, so for very low dark matter mass and for very heavy dark matter mass, going underground is the best way forward. Okay. So now, just before concluding the talk, I will take one or 2 minutes to just give you one more idea, and then I will conclude. So far I have talked about primordial black holes as dark matter, and how to test WIMP interaction with neutron star. I will try to talk about one more interesting scenario to try to connect gravitational wave observations with the particle dark matter. So the idea is as follows. Recently, LIGO-Virgo collaboration has reported some unusually low mass objects. For example, you might have seen this in the news that there are some LIGO-Virgo collaboration has observed some events where the masses are very exotic. For example, this celebrated event GW190814, where one of the mass is around 2.5 solar mass, and no one knows what is this thing. If it's a neutron star, then it is the heaviest neutron star that we have ever observed. If it's a black hole, then it is the lightest black hole that we have ever observed. So the point is, we have recently started to observe some unusually low mass object, and we do not know what is this thing. So as I told you in my earlier slide, that suppose you have a neutron star, and suppose you are talking about non-annihilating dark matter, then what happens? The neutron star capture non-annihilating dark matter, and there will be a black hole formation inside the neutron star. This small black hole eventually eats up the neutron star, and therefore it will create a black hole. So the final mass of the black hole is essentially the final mass of the neutron star. And since low mass neutron star exists, so from this thing you can produce actually low mass black holes. So the point is, the point is, dark matter accumulation inside compact stars can lead to low mass black hole formation, and you also know that low mass black holes are very hard to produce, so this provides an alternative channel to the low mass black holes. Okay, so maybe I should now conclude that particle dark matter interaction in stellar object is a novel astrophysical probe of dark matter interaction with nucleons. Non-annihilating dark matter with non-zero interaction strength with nucleon can actually produce low mass black holes. With remarkable advances in gravitational wave astronomy, we have already started to observe unusually low mass black holes, and we can test their origin. Okay, thanks for your time.
Yeah, thank you, Anupam, for this nice talk. We can take 1 or 2 questions due to time constraints, if there are. Okay, I don't see any questions here. So thank you, Anupam, very much for staying awake and giving this nice talk.
Thank you again. Thank you.
Okay, then we move to now Subham. If you can start sharing your slides.
Can you see my slide and hear me fine?
Yes. Yeah, please.
All right. So hello everyone. First of all, I would like to thank the committee for giving me such a great honor, and also thanks to Dr. Seema Sharma for her guidance throughout my doctoral research. In this presentation, I will talk about my thesis work. As all of us know, the Large Hadron Collider machine collides the beams of proton at TeV energy scale, and it has been taking data since 2010 in different runs. We are currently at run 3, which will go on for another couple of years. And after that, the LHC accelerators will be upgraded and its instantaneous velocity will be ramped up. This era is called high luminosity LHC, and it is expected to start later this decade and will deliver 10 times more integrated luminosity with respect to LHC. The advantages of this is that we will have more statistics for Higgs and other standard model precision measurements, and will provide us opportunities for searches for beyond standard model physics. However, the detectors will face various challenges, such as very high radiation dose, as well as high pileup condition. For example, the average pileup will range somewhere from 140 to 200 per bunch collision. To cope with such harsh environment in HLHC run, the forward region of the CMS will be replaced by a highly granular calorimeter called HECal. The HECal is a sampling calorimeter. The electromagnetic part of it is called CEE. It will use silicon as the active layer, and copper, tungsten, and lead as the absorber, and it will have 28 sampling layer with a depth of 25 rotational length and about 1.3 interaction length. The hadronic part of it is called CEH, and it will use silicon and scintillator as the active layers and steel as the absorbers. It will have 22 sampling layers with a total depth of 8.5 interaction length. The HECal will cover the end cap part of the detector and will have staggering amount of readout channels, for example 6 million for silicon and about 250,000 for scintillators, and will offer a precise timing measurement with a resolution of 50 picosecond. The design parameter of the HECal has been chosen such that it ensures the optimum physics performance throughout the HLC operation, and it is capable of doing 5D calorimetry, that is measuring 3 position measurements, 1 time and 1 energy, which makes it ideal for the particle flow reconstruction concept. HECal is an imaging calorimeter, meaning that it can produce detailed images of shower evolution, which makes it extremely useful for the event characterization. For example, in these images, I have shown a shower from photon and a jet originating from vector boson fusion process, which is the second dominant Higgs production mode at the LHC. And in these images, you can clearly see the photon shower and jet in HECal layers. This will allow us to cleanly trigger on VBF events, resulting in higher Higgs event statistics and resulting in smaller uncertainty on the Higgs measurements. So HECal, like any other detector, goes through various stages. The first one is the conception, where the requirement, detector design, electrical and mechanics are laid down, and the performance is studied based on simulation. The next step is the prototyping stage, where the sensor and detector prototypes are fabricated, and the performance is studied based on real data, and the design is improved in multiple iterations if required. The final stage is the installation, but for the HECal, we are currently in the prototyping stage. For each sensor module prototype, it has to undergo quality assurance test, and it is rejected if it fails in this test. This is called system test, and I performed such a system test for silicon sensor prototype version 2016 at CERN. These two images here show the system test setup. Here I made the electrical characterization and connection and communication with the DAC was performed. I measured pedestal and noise level, and finally measured the energy deposited by cosmic pions in cell. For example, this plot here shows the ADC distribution for a single channel. This peak here corresponds to noise, and the right one corresponds to the energy deposited by the muons. We then built a large-scale prototype and tested it in the beams of particles during October 2018 at S2 beamline CERN. This image here shows the picture of the experimental setup. The first part of it is the CEE prototype, which is the electromagnetic section. It was built in hanging file structure. It had 28 sampling layers with copper, tungsten, and lead as the absorbers, with a total depth of 28 radiation length and about 1.4 interaction length. Brand CEE, we had CEH prototype. It had 12 sampling layers, and the modules were arranged in daisy-like structure. It used steel as the absorbers with a total depth of 3.4 interaction length. We also used AHCal prototype from Callius collaboration, which is based on scintillator on SIPM technology. It was there to mimic the scintillator part of the HECal. It had 29 sampling layers, and it used steel as the absorbers with a total depth of 4.4 interaction length. So this was the first large-scale test where we employed 94 silicon modules for the HGL, and it had about 12,000 channels for the silicon and about 22,000 for the scintillators, and the whole setup was exposed to beams of positron and charged pion of energies ranging from 20 to 300 GeV and muon beam of 200 GeV. So we recorded more than 6 million events over a span of 3 weeks of data. Taking these images here show the event display for the muon on the top, positron in the middle, and charged pion on the bottom. And the goals of this experiment was to build and test a large-scale prototype, test readout electronics, measure signal-to-noise ratio of the silicon sensors, study the physics performance to electromagnetic and hadronic showers, and vet the simulation modeling. We first begin with the channel-to-channel response equalization, because different cells may have different response to identical traversing particle. That could be either due to differences in actual depletion width or differences in the gain settings of the readout chips. So to equalize the response, we used minimum ionizing particles, and for that we used 200 GeV muon beam as the proxy for the MIPS. For example, this plot here shows the high gain ADC distribution for a single channel, which we fit with the model, which was Landau convoluted with Gauss, and we extract this peak as the calibration constant. Using this strategy, we calibrated about 85% of the silicon cells in CEE and CEH. Furthermore, we estimated the signal-to-noise ratio of these silicon cells, which essentially tells us the level of separation between signal and inherent noise in these sensors. This plot on the bottom shows the SNR distribution for 2 types of sensor thicknesses that we used in the experiment. These are important inputs for the future sensor module designs. Using these channel-to-channel calibration factors, the energy is reconstructed in MIP equivalent of energy deposit for each hit. Also, the readout chips that we used, which is called Skyrock to CMS, it provides different ADC gain stages, namely high gain and low gain, and another measurement called time over threshold, which allows a wide dynamic range of energy measurement. And we performed an inter-gain calibration to ensure a linear response over large dynamic range. These 2 plots here shows the correlation between high gain versus low gain and low gain versus the time over threshold or TOT. And we observed sufficient overlap between these gains, and we fit a straight line in the linear region and obtained the fit coefficients as the intergain calibration factors. Okay, so now having reconstructed the energies in terms of MIPS, we move to physics performance to hadronic showers, for which we use the data from the HCAL prototype from Callius collaboration. And we begin with first identifying the depth of first hadronic interaction. Because of the high granularity of CEE and CES prototype, we could identify the location of first hadronic interaction of pion, where it initiates showering. For example, this image here shows the pion entering from the left, initiates showering in the CEE and deposits its energy in different compartments. For that, we developed an algorithm and optimized it using GR4-based truth information, and this algorithm was found to be more than 90% efficient in correctly identifying the shower start location within 2 layers. The plot on the right shows the shower start location as a function of calorimeter depth for data and 2 models of simulation in different colors. And we observed an exponential falling behavior as expected, and a good agreement between data and MC was observed. Okay, then we reconstruct the energy of the pion showers. Since different compartments have different sampling fraction and different absorbers, therefore we had to optimally combine the energies. To begin with, we used calorimetric energy scale, that is MIP to GeV convergence scale for the electromagnetic and hadronic sections, using 50 GeV positron shower for the EM section and 50 GeV pion shower for the hadronic section. This plot on the top shows energy distribution for 200 GeV pion for data and 2 simulation models. We observed that the simulation fairly well reproduces the distribution of the energy, but it is slightly higher than the data. We then obtain energy response by fitting a Gaussian around the core of the distribution, and the plot on the bottom shows the energy response as a function of beam energy. For the pions, we start showering CEE, and we observe a non-linearity in the response, which tells us that this is a non-compensating calorimeter. And we also observe the response is less than 1 for 50 GeV pion, which tells us that the E over H ratio is greater than 1, meaning that this is an undercompensating calorimeter. The non-linearity is also fairly well reproduced by the simulation, and the level of response is systematically higher for all the beam energies, which we fixed by applying a global scale factor. Now this non-linearity in the energy response can be fixed by using energy dependent weights. So for that, what we did was we combined the energy measured in different sections along with some calibration factors, which is energy dependent. And to obtain these weights, we constructed and minimized this chi-square analytically. These weights were obtained using TB data, test beam data, and are applied on both data and simulation. These two plots here shows the energy response on the left and resolution on the right. And we observed that after applying the optimized weight, the response was linearized. Also, we observed that the data and simulation show good agreement between each other for both response and resolution. Finally, we studied the shower development in the GCAL prototype, both for the longitudinal in the longitudinal direction as well as in the lateral direction. For the longitudinal shower shapes, we studied it in terms of mean energy deposited, in terms of MIPS as a function of calorimeter depth. For example, as I've shown here on the left, we observed various features in these longitudinal shower shapes in data which was fairly well reproduced by the simulation. The most striking feature we observed was that the shower peaked rather early in CEE for early showering pions. And our study showed that this corresponds to the electromagnetic component, basically neutral pions of the hadronic shower, which in future can be exploited to compensate this event by event neutral pion fluctuation. For the lateral shower shape study, we studied it in terms of energy contained in cylinders of different radii in different compartments. This plot here, for example, shows the transfer shower shapes for CEE and CEH for data and compared with two simulation models. So both longitudinal as well as transfer shower development was reasonably well reproduced by the simulation. All right, so this test beam that we did in October 2018, it was a fairly well executed campaign. We achieved all of our goals, which has been published in different papers, and such detailed performance studies with the real data and simulation validation are crucial for the HLRSC physics program, and these studies have shown that the HGCAL can deliver as per expected performance. That brings me to my final slide. So to summarize it all, the HLRSC provides good opportunities for finding new physics in direct searches as well as testing the limits of standard model. It also poses various challenges for the detectors, and the CMS collaboration has planned a comprehensive upgrade program for the LHC. And for example, for the NCAP calorimeters, it will be replaced by a highly granular calorimeter, which is capable of doing 5D calorimetry because of its unprecedented granularity. The CMS HGCAL team performed beam test experiment during October 2018, which I have described in my thesis. And extending the work of this thesis, the CMS group at IISER Pune, basically at 9 company, have already achieved much better pion performance using sophisticated machine learning algorithm. For example, this plot here shows the improved performance of the pions as compared to the original method. So we have exciting times ahead for particle physics community. Thank you.
Thank you very much, Shubham, for this nice talk. If there are one or two questions. Okay, there are no questions from the audience here. So thank you again, Shubham, for staying up late in night and giving this talk. Thank you.
Thank you.
So now we move to the next talk by Biswajit.
Can you see my screen?
Yes, please go ahead.
Yeah, first of all, like I like to thank all the selection committee for really considering me for this Rahul Basu award and giving me the runners up award. So like my thesis work is like in theoretical physics, and like I worked on kind of deriving soft graviton theorem and some prediction of gravitational tail memory, which I am hopeful to be like one can observe it in very recent future. So okay, like first I want to thank actually all my like faculties with whom I collaborated and being supervised and like benefited from like with like many discussion sessions from my official supervisor Dilip Jatkar, Ashok Sen, with whom I collaborated in most of the projects, and also with Alok Ladda on various discussions on soft theorems. I also want to thank all my like student and postdoc collaborators with whom I collaborated during my PhD, Subhanil Chakraborty, Sitendra Kashyap, Mrityunjay Bharma, Sayali Bhatkar, and Arnapriya Saha. So with that, let me talk about my topic of research and contributions made in the thesis in a more simple way without not showing too many equations. So in my thesis, basically we took a small step towards like deriving gravitational waveform using scattering amplitude technique. As you know, like in LHC, like people measured like various scattering cross section, decay rates of particle scattering, which are very subatomic particles, and they are the tool what one use in quantum field theories like scattering amplitude. On the other hand, in suppose in LIGO, one observes gravitational wave like setting up some like detector system on the Earth and looking for far away objects like black holes, and these are like some heavy objects, and the distance is order of like many light years. So these two seems like completely different kind of subjects, but actually they are not. In a sense, we can even derive like this gravitational waveform using the similar kind of technique what we learned in quantum field theory, which is the scattering amplitude. In a sense, like you can think of like if we try to scatter, suppose to going to two particles with some graviton emission, and then we can relate this thing actually to compute even the gravitational waveform for a classical scattering process in properly classical limit. So this is kind of the kind of work which I pursued in my thesis. So let's start with the classical problem, like basically asking the century-old question, like consider some scattering event, like with like many number of massive particles and some massless particles coming in with like producing some final particles with some gravitational radiation. And we are sitting on Earth with our detector, say LIGO, at distance r from the scattering center along some direction n hat. And the question which we want to ask is like what will be the gravitational wave pattern at large distances, or you can, in other language, you can think how much the space-time metric deviates from the flat space-time and how this deviation varies with time. So this is the kind of question we want to ask, and we can probe it with the gravitational wave detection. For example, like a qualitative pattern of gravitational waveform for a black hole merger process, you can see when the two black holes are very far apart, they are in spiraling, the waveform looks like kind of oscillatory, and when there you can use like post-Newtonian analysis, which is kind of a relativistic like the velocity expansion, small velocity expansion, which is relativistic expansion, and then when they really come close, they merged and they try to form a single black hole, then basically the gravitational strength is very strong. You have to use numerical relativity to study this process. Then after that there will be some bring down phase where quasi-normal modes will die out, and this, to understand this, one use the theoretical tool which is called black hole perturbation theory. On the other hand, what we developed is that even after this bring down phase, there still the gravitational waveform, or you can think of the distance between the mirror of the gravitational detector, don't settle completely, but actually it still like varies, the distance varies with time, and finally it settled to a different position than the like the initial position before the mergers happens. And this feature is known from long back as known as gravitational memory, and what we tried to show is that this gravitational memory we can compute using a special properties of scattering amplitude, which I will like call at soft theorem, and this is the kind of technique what we developed in my thesis. So the classical question is that we want to compute h mu nu, which is the deviation of the metric fluctuation from the flat background, and where u is kind of the retarded time, which you can think of the time passed after the peak of the gravitational wave passes through your detector. And we are interested with the transverse traceless mode, which are the physical degrees of freedom of this gravitational fluctuation. And we are only interested in the 1 over r, which is the radiating mode of the gravitational waveform at large time, like large retarded time u, which is the, in the waveform pattern you can see the last part of the waveform. And what we derived is that this Hij transverse traceless mode has a constant piece, which tells us like that even after passing the gravitational wave, there is still a permanent displacement between the mirrors of the detectors, which was not present in the earlier case, which is a difference between the earlier displacement and the later displacement. And with this we can also say that how the mirrors of the detectors really reach this permanent displacement. What is the, like, is it varying with power law, and if power law, what is the coefficients? Like, in a sense we determined the 1 over time coefficient and some log of like retarded time over time square coefficient, and also 1 over time square coefficient. So let me go in little detail what these coefficients are. So for example, this Aij, which I just mentioned, it's called known as like static gravitational memory, which gives the permanent change of the distance between the two mirrors of the gravitational wave detector. And Strominger from Harvard, he came up with the proposal that actually this Aij can be related to a particular form of Weinberg's soft graviton theorem. What this soft graviton theorem is, you take an amplitude with some number of particles coming in and some number of particles going out with some external graviton is emitting, and you take the frequency of this external gravitons, or the energy is very small, then you can see that this amplitude you can relate to amplitude which don't contain this graviton at all, and the graviton information is completely carried in this soft factor, but this is only valid in the low frequency expansion, and Weinberg derived the leading soft factor and which predicts this coefficient Aij. So what we did, we basically tried to see that, okay, what like beyond this Aij, what could be the further corrections, and what we found is that not only this Aij, we found the Bij, which is called the tail memory, which basically tells that how really this permanent displacement position is approached from large time, the large time behavior, and it is known as the tail memory. And this is actually, this coefficient is completely determined by the scattering data, by the asymptotic momenta and the scattered, like asymptotic moment of the scattered object and the direction of the gravitational wave emission. And what we found is that we can relate this thing to a subleading soft graviton theorem, which is a correction to Weinberg's soft theorem at the subleading order, and this have some logarithmic of the frequency of the graviton emission. Then we just did not stop there. We also tried to compute the further corrections like the Cij, Dij, and we also find that like these are tail-to-tail memories, and like some, if the scattered object carries some spin, there will be some spin-dependent gravitational tail memory which contains in this Dij terms. So with this all computation, like what are like we going to do? So obviously what we do is that we know this coefficient exactly for some general scattering event, but we can try to see, like, or can try to do some order of magnitude estimation for some physical, astrophysical scattering event, like say core polar supernova, hypervelocity stars, or even neutron star merger. And interestingly, what we found is this strain of the gravitational, like strain of the gravitational radiation, which is the change between the distance of the mirrors and the original distance. And what we found is that this turns out to be like 10 to the power minus 23, which is almost in the edge of the current detector resolution of say LIGO. So we can hope that certainly we can observe these tail terms along with this memory in the future detectors like LISA. And another interesting observation what we found is that for black hole merger process, we try to write down our general formula, the coefficients, what we found is that this tail terms actually completely vanishes for black hole merger. So this gives a new prediction from general relativity that one should not observe any of these tail effects for a black hole merger process. So with all these like interesting like highlights, let me go in little deep and try to see how we derive this result. So let me talk about the quantum scattering amplitude setup, or what is really the soft theorem. It's basically you consider an amplitude which has arbitrary number of finite energy particles, which you used to call hard particles, and with some arbitrary mass, and they can have arbitrary mass and spin. And this amplitude also contains as external particles some low energy photons or gravitons, which we call soft photons and gravitons, and take this amplitude, and we can write this amplitude in terms of amplitude which don't contain any of these soft photons or graviton if we expand them in power of the soft momentum. In a sense, this gamma n plus 1 is, you can think of like n hard particle and say 1 soft graviton amplitude, and you can expand in terms of the where epsilon is the polarization of the graviton, k is the momenta, and you do a small k expansion. And what we found is that this can be written as an amplitude which don't contain this external graviton, and this factorized terms which are like S0, S1, where S0 is the leading soft factor which is derived by Weinberg, and this S1 which is derived by Kachajo-Strominger, which goes like omega to the power 0. But this result is only valid in 4th space-time dimension for tree-level amplitude, not for loops. And for d greater than 4, it has been shown that those are valid even for loop amplitudes by Ashok Sen. But then still the subtlety remains that we are in 4 dimensions, and what will be the soft factorization result in 4 dimensions for a full loop amplitude, not only just tree level. And this is what we really resolved in our work. So basically what we did, we basically take some loop amplitudes of say n plus 1 particle scattering. Here I just drew the 4 plus 1 particle scattering and divide by the 4 particle scattering and take the momentum of the graviton to be small and try to extract the soft factor at the subleading order. And what we found surprisingly is that it is not like a polynomial expansion in omega, like omega to the power 0, what people found earlier, but actually it contains a logarithmic in omega term. And this behavior, like to get this behavior, it's not really easy. That's why people did not able to do it earlier, because of the infrared divergence property of the scattering amplitude in massless theory. So in the way we developed technique how to take care of the infrared divergence of the scattering amplitude and how to properly factorize and cancel between the ratios of the amplitudes. So with this, like, let me go to describe how the class in the independently we can also derive the waveform in a directly classical scattering process. And there what we consider a setup is like some particles are coming in with some momentum and spin, they interact with some strong interactions inside in a finite region of space-time, and then say they disperse to some other number of particles with some momentum and spin, and then this region where they are strongly interacting, say this region has a length scale of L. The question which we asked is basically we want to determine the waveform with a retarded time u which is much greater than L, which is like by Fourier transform related to the fact that we want to determine a gravitational waveform with frequency which is much less than the L inverse. So the wavelength is much greater than the length scale L. And to do that, we have to first really identify this kind of some dimensionless parameters in the theory, which are like Newton's constant time mass of the scattered object times frequency and some spin and different combinations. And then what we did, we basically developed an iterative procedure considering the Newton's constant, which is actually known as the post-Minkowskian expansion, and we basically solved the Einstein's equation to get the corrected metric, and then substitute the corrected matrix in the geodesic equation to correct the trajectory. And once again with the corrected trajectory, we can also compute the energy momentum tensor and substitute it and find that, like, solve the Einstein's equation. So in this iterative way, we can actually compute up to pretty higher order in the Newton's constant all the gravitational waveform, and at the end we want to take the small frequency limit to extract the gravitational waveforms, which I tried to show earlier. Or in a sense, here I wrote down the result once again. So you take the time Fourier transform of the gravitational fluctuation, and like it's the 1 over r component of it, and what we found is that that has a 1 over omega and a log omega, and also at 2 loop order omega log omega square, or in the classical limit is the second iterative order, or also the spin dependent omega log omega piece. And then we did a Fourier transform in omega variable, and we actually reproduced what I showed earlier, the gravitational waveform, which is some constant memory and some tail memory, tail to tail memory, spin dependent gravitational memory, all these coefficients exactly. And interestingly, all these coefficients are universal. In a sense, they are only determined by the scattering data, like initial final momenta, impact parameters, and spins of the scattered object. So with this, now I showed like a different computation from scattering amplitude and a computation of gravitational waveform from a classical scattering process. What are the relations between them? And we found also the relation is that if you do a Fourier time Fourier transform of the waveform and you contract by the polarization of the graviton, it turns out that it is proportional to the soft factor derived in the quantum scattering process. And if you have to take proper classical limit of the soft factor. So the soft factor contains also some quantum corrections. If you take proper classical limit, you will find this relation. The waveform is proportional to the soft factor derived from the scattering amplitude. So in a sense, if we know how to do scattering amplitude more and more loop orders, just from there we can read of the low frequency gravitational waveform using this formula. So with this, here just I gave a table what we did and what I could not. For example, you see we like the gravitational waveforms are written in green and the kind of in frequency space, and the late times are written in sky blue. And you can see the blue ticks are basically the coefficients which you derived from both ways, scattering amplitude and classical scattering, and the like the stars, orange stars are basically this, we conjectured the forms like looking at the structure and give a partial way of the strategy of computing them. And the red crosses are the things what we could not able to derive yet, but this is kind of like people can try to derive, and these are all important in the current era of gravitational wave physics. So with this, let me thank you all.
Nice talk. Let's see if there are any questions or comments. Okay, there is one. I will translate it to you.
Vedant, I have a question.
Yeah.
Vishwajit, which do you think is the first prediction which can actually be experimentally verified?
Which in the gravitational memory?
In what you have done in your thesis, which is the first prediction that you think can be experimentally
Okay, yeah. So I think you see the first predictions will be really observing this coefficient Aij, which is the constant gravitational piece. Like if you wait for long time and you measure the distance between the detector, like the mirrors of the gravitational detector, it should be the first observed. But with this, what we found is the tail term, what we computed this 1 over u, all the coefficients, those also, if you, like for example, let me give one proper example, like say how neutron star production happens in a supernova explosion. So in a supernova explosion, when you when a type 2 supernova explosion, when a neutron star produces, it gets a huge kick velocity. It's like 5,000 kilometers per second. So there must be some particle or some object which is just by momentum conservation is emitting in the opposite direction. So people have two kind of models for this kind of thing. One is kind of some excess neutrino which gives this kick velocity, and another is like there is some massive objects which give this kick velocity. Now suppose our prediction take the 1 over u tail term, you will find that if some massless neutrinos like give this, or almost massless neutrinos give this kick velocity, you will find this tail term vanishes. On the other hand, if it is a massive object, then actually these tail terms remain. So if you can observe for a neutron star production case in a type 2 supernova explosion, from there you can able to see which model is correct. This kind of give a really kind of observational thing. And you see the the delta L by L which I computed, it's pretty observable in 10 years, like in 2035. If they are projecting this LISA observation can start, one can actually observe all these memory terms pretty well. So in a sense, this is the theoretical work. It has a lot of physical implication ahead.
Okay, thank you so much. Although I mean, the U log U kind of things are really difficult to observe, isn't it?
No, actually, okay. I think you see. Yeah, I think let me then point it out. Okay, those are actually also observable. So maybe just let me go back to first slide. So you see, there is a 1 over u. So what is u? U is the time up, this u is the time of the after the peak of the gravitational wave passes, you have to wait for the time. Now suppose if you take this u to be small, after the peak of the gravitational wave passes, if you take, one can see how validity of this formula. It turns out that for kind of a observation, the supernova observation is kind of few seconds only. So if you wait just for a few seconds, and if this u is small, it turns out that Aij and the ratio of Bij and u are in the same order. So even if you can observe the permanent displacement, you can also observe the tail effect.
I see. Thank you.
So actually all these order of terms with if you take small u's, those are all same important than the compared to the leading memory. So
as compared to the Aij. Okay.
Yeah.
There is one question here.
Just a small question. So since I'm not in the same field, I might have missed it, but in the beginnings in slide, he was showing the question, he was asking about the deviation in the flat space-time metric and its dynamic property. So how does he relate? What kind of deviation did he see, if at all, and the nature of it?
So you want us to go to the initial slides? Or?
Yeah, how did he answer that question? How does it relate to this after slides? I couldn't put the connection.
Okay, can you
Can you go ahead with the slides and let me come to which one are you
yeah.
referring?
Yeah, just the previous.
Previous one. Previous slide.
Yes.
Yes. Previous, just before this.
One before?
One before.
One before. One slide before. Yeah.
Yes.
Yeah, the question in the red. So
she wants to know a little bit more about the last question on the orange.
Right. So how does it connect to the work? And
so can you please
last question which you have written in orange on the
yes.
right hand side connect to your work?
Oh, sorry. So basically, you see, what is this H mu nu? H mu nu, or the gravitational fluctuation. What I told you, it's just basically the difference between the metric to the flat metric, right? So what I want to know is basically the compute this H mu nu, and I want to know how this H mu nu varies with time. And now you can tell that how this H mu nu is related to, suppose what I am telling, like the distance between the mirrors. Because how you really observe in a LIGO detector, there is some kind of like interference patterns happens, and light, or you can see the lasers basically pass through, and then they basically pass through in a proper path, like it's kind of like you have to compute the distance ds square, which is like g mu nu dx nu, and g mu nu knows about the metric. So if the background metric changes, then basically the path also changes. So basically, if you can compute h mu nu, then you can just substitute this formula, and you can see like how the light travels. And if there is a curved background, then possibly it will take more time if it increases from the flat background, and then the interference patterns will change. So in that way, like this gravitational fluctuation and the observations is like kind of related, or whatever I'm telling, the distance between the mirrors will change, that you can measure just from the interference pattern also. Yeah, I don't know whether I gave the correct answer to the question.
Yeah, thank you. Okay, then let's thank Biswajit for this nice talk and getting up early in the morning, I think. Thank you. Now the next one is by Samir. Samir is present here, so let me. You have to stand here so that both Zoom and people can see. Okay. Okay, this is yeah. Because then both. You all can see the slides on the Zoom.
Yes, we can see them.
Okay.
At least I can see them.
Okay.
I can see them too.
Okay. I hope everyone can hear me in the audience here and also from Zoom. Okay. So my thesis is titled "Search for Lightly Ionizing Particles in Super CDMS and Simulation of Neutron Backgrounds." This work is based on these 3 publications which I have listed here. I have done my thesis from IISER under the supervision of Professor Mohanty. Okay. Hello. Hello. Okay. Before I discuss my thesis, I would like to express my sincere thanks to IPA Professor Rahul Basu Memorial Award Committee for selecting my thesis for honorable mention. I am deeply honored for this. I would like to express my sincere thanks to DAE-HEP Organizing Committee for giving me this opportunity to present the work here. I thank my supervisor, Professor Mohanty, for guiding me in my PhD period. Without his support, this thesis wouldn't have been possible.
I also thank my colleagues from IISER and from Super CDMS collaboration. They helped me during my PhD period in different ways. With this, let's talk about lift search analysis with the data taken in Super CDMS experiment. I'll start with a brief motivation. So, lifts are basically particles with fractional electric charge. There are several experiments which are searching for these particles. Because of the small fractional charge, they deposit very small amount of energy in the detector, hence they are called lightly ionizing. So, in this right hand side plot, in y-axis mass and in the x-axis inverse of fractional charge excluded by different experiment and astronomical observations. Similarly, in the bottom plot, this is the intensity upper limit as a function of fractional charge excluded by different direct detection experiment. If I want to explain one particular curve, for example, the results from this Texano experiment. So, all the region above this red line is excluded by this experiment. So, they have excluded from charge E by 1000 to E by 3 times 10 power 5. Super CDMS is primarily a direct detection dark matter search experiment. Measures very small amount of energy that particle can deposit in a detector. This experiment is also sensitive to fractionally charged particles. So, in this analysis, we have calculated intensity, upper limit of intensity as a function of fractional charge for different masses and different incident beta gamma, where beta is velocity per speed of light and gamma is Lorentz factor. And the charges we excluded a large region starting from E by 100 to E by 10 power 8. Here I would like to mention that all these direct detection limits or all past direct detection experiment assume that lifts are minimum ionizing, which basically means that beta gamma is nearly 3 or beta gamma is nearly 3, whereas in this analysis we are exploring a really large regions where, like in the low end, 0.1 is close to a non-relativistic velocity, and here we go to very high energy incident particles. Okay, about super CDMS. So, this is super cryogenic dark matter search experiment. They employ semiconductor germanium detector. Each detector has a mass of 600 gram. The detector measures phonon and charge signals from particle interactions. So, there are 4 phonon channels, this triangular regions and this outer ring, and 2 charge channels, this inner disk and the outer ring. So, what happens when a particle enters the detector? It can gives recoil to the nucleus or electrons inside the detector material, and the primary interactions produces phonons called primary phonons, and the interaction can also ionize the atom, producing electron and holes. The detector, so across the on top and bottom side, a bias voltage is also applied to the crystal. So, the charge carriers produced from these interactions, they traverses to the respective electrodes and they are eventually collected, and the work done by the electric field to move to traverse these charge carriers is produces phonons are called Luke phonons. So, both these primary phonons and this Luke phonons are collected in the phonon channels. So, here one thing to notice is that this Luke phonon contribution is proportional to the bias voltage. So, greater the bias voltage applies across the crystal, more amplified will be the signal. As a result, you can measure very small energy deposition in the detector. This mode of operation is called CDMS light mode, where typically a bias voltage of 70 volt is applied. Particularly in CDMS light run to energy deposition threshold as small as 56 electron volt was achieved.
Okay. So apart from measuring the data in the from the experiment, there is another major part in this analysis, which is the simulation. So I have tried to present the entire analysis in this in a flow diagram here. So there are two major parts: simulation and data. From data, we make some applies the data measured in the detector. We apply some cuts, calculate efficiency of the cuts, and then you get the final spectrum of energy deposition in the detector. And from simulation, we calculate the expected energy deposition distribution. But there is one major challenge, which is the following: that fractionally charged particles were not defined in any simulation package available. It's not defined in, for example, GN4. So we had to define this particle, positively and negatively charged particles, in a way that we can perform simulation with GN4. We write a physics list where we specify all the processes through which these particles would lose energy in the detector, and then we will validate energy loss for different charge, mass, and incident velocity. After the validation, then only we calculate the expected energy deposition distribution. Then the expected distribution from simulation and the measured distributions from data, they are compared, and the upper limit on the intensity of this particles are calculated. Okay, let's first understand how any general charge particles loses energy in a detector, for example, muons in germanium, and then I will explain what changes as we go to fractional charges. So in this plot, in y-axis stopping power or average energy per unit length, average energy loss per unit length plotted as a function of incident beta gamma or momentum. Here you can see that in the low energy region, ionizations is a dominant process of energy loss, and here is a minima. This is the region we called minimum ionization region. And as you go towards high energy region, processes like Bremsstrahlung shown in this green curve, and pair production shown by this red dashed line, they become important. Lifts, since they are also charged particles, they are expected to lose energy through all these processes. However, there will be some dependence on charge, mass, and beta gamma, which I am showing here. So, for example, ionization. So the stopping power for goes as the charge square of the particle. So for a fractionally charged particles, so this will be suppressed by the charge square factor. To show the charge dependence, here in the y-axis I have plotted d dx multiplied by the inverse charge square. I have considered charge E by 1000 here, and I have plotted for ionization two different masses, 100 MeV per c square shown by the open circular markers, and 1 GB per c square shown by the triangular markers. So this shows that since they fall on the line, this solid, this dashed line, which is the energy loss by muons. So they say that, so this plot shows that the dx charge dependence is respected in the simulation. And for a given beta gamma, since 100 MeV and 1 GeV, the energy loss coincides. So this means that for a given beta gamma, the average energy loss is same from ionization. In Bremsstrahlung, there is a, apart from the charge square dependence, there is a mass dependence, inverse mass square dependence, as can be seen in this plot. From 100 MeV per c square to 1 GeV per c square, when you go from this mass to this mass, this reduces by a factor of 10 square. Pair production, here again stopping power as a function of beta gamma. So we see that the charge square dependence is respected in the simulation, and also for a given beta gamma, the energy loss for different masses are same, which basically independent of mass for a given beta gamma. So with this, after this validation, we calculated expected energy deposition distribution. So in this top plot, I have plotted the probability in the y-axis and in the x-axis energy depositions. I have considered one beta gamma of 0.3.1, but 3 different fractional charges, E by 200, E by 500 and E by 2000. So we see that as we decrease the charge of the particle, the probability of energy deposition also decreases. And in the bottom plot, here I have shown for a given charge of E by 500, but 2 different beta gamma of 0.1 and beta gamma of 3.1. Here we see that when beta gamma is small or when velocity is small, larger energy depositions are more probable as compared to the smaller energy deposition. Okay, so this was the expected energy deposition distribution, and from experiment we measure the measured depositions in the detector. So here, but to get to this stage, we need to go through these few steps. So from detector we measured raw pulse, which is then fitted with a template, and from optimal filter algorithm we calculate amplitude, on which we then apply calibration to get the energy deposition in physical units. We apply some quality cuts to get this final spectrum. So this measured spectrum and the expected distributions are compared, and intensity upper limits are calculated. So intensity is nothing but the number of lips that number of particles which are lips that we think are passing through the detector per lifetime of the detector, and this geometric factor and detection efficiency. So in this right hand side plot, I plotted the intensity upper limit as a function of inverse fractional charge for minimizing lips. So this is our results compared to all the past results. So we see that for all charges below E by 160, we have the best limits, and the lowest limits that we achieved is here at E by 160 again, and this is 1.36 times 10 power minus 7 per centimeter square per second per steradian. And in this bottom plot, this is intensity as a this is the same limit but for different incident beta gamma. So this is also a new, so we explored a region of beta gamma beyond minimization, which was never explored in experiment. Okay, so with this I come to the next topic of my thesis, which is simulation of neutron backgrounds for a India-based proposed dark matter search experiment at Jadugara Underground Science Laboratory. So at Jadugara Underground Science Laboratory, so this would be the first phase of a proposed dark matter search at INO. This is under a hill of depth 500 meter around. So in this plot I have shown the hill profile in the in the z axis. In this axis, this is altitude, and this is latitude, and this is longitude, and the vertical depth is around 1.6 kilometer water equivalent. Here in this bottom plot, the entrance of the Jadugara cavern is shown. The main rock composition around the cavern is uranium, thorium, silicon, oxygen, aluminum, and so on, as listed in this table. Okay, so in dark matter search experiment, including the one which would be at JUSL, neutrons will be a major concern, because neutrons can easily mimic a dark matter search or a dark matter sequence. So it is important to understand and quantify the amount of background that is expected at the experimental site. So how these neutrons can be produced? So there are two major ways this neutrons could be produced. One is cosmogenic neutrons, and the other one is radiogenic neutrons. So cosmogenic neutrons are primarily produced from muon interactions with the hill rock material, radiogenic neutrons are produced from alpha reactions where alpha from the uranium and thorium traces present in the rock, they interact with the light material producing neutrons. The spontaneous fission of uranium and thorium and neutron-induced fission can also produce neutrons. Okay, so we calculated both this cosmogenic and radiogenic neutron from a GN4 based simulation. Here I have tried to show how the cosmogenic neutrons are calculated. So there is one major challenge in doing this computation. This is because like all tracks originating from the surface of the hill may not reach your experimental cavern site. So this means we need not simulate all particles starting from from its origin, and also the neutrons which are produced very far from the experimental cavern site, they will also not be able to reach the detector. So how we optimize this is the following. So we first sample event on the surface of the detector within this radius of 1.5 kilometer. We calculate muon lateral displacement and maximum distance traverses by muons as a function of energy. From this information we calculated this solid angle within which we only track all the particles coming from the surfaces. All the particles where the tracks are far from this solid angle, they will not be tracked in the simulation and in this way we can save a lot of computation power. And we also studied how the neutrons produced from this muon interaction traverses through the rock materials. We calculate transmission probabilities, and from that we determine the optimum thickness that we need to consider for the simulations. Neutron produced beyond this thickness we do not track in the simulation. Okay, so with this we calculate the flux inside the experimental, both the muons and neutrons produced from the muon interactions. So this is a plot of muon distance traverses in the rock as a function of energy. This solid circular markers are the maximum distance muon traverses, and this is the average distances muon traverses. From this we learn that muons with energy greater than 300 GeV can only reach the cavern, and also from the taking into consideration the lateral displacement of muons for different energy from this curve, that the muons traversing within the solid angle of within the angle of 3.1 degree will only reach the cavern. Okay, so with this we found that the flux of muons that reaches inside the cavern is around 4.45 times 10 power minus 7 centimeter per centimeter per second. Here is the distributions of muons at the cavern shown by this black histogram, and the starting muon energy distribution was this blue histogram. And the flux that we estimated, that muon flux, this is comparable to the number calculated at a similar depth in weak salt. Okay, and to compute the neutrons produced from muon interactions, so this is the transmission probability in the y-axis as a function of rock thickness. So we see that the transmission reduces as we go more higher thicknesses, and beyond 200 centimeter the neutrons do not contribute significantly to the neutron flux. So we considered only 2 meter thickness of rock, and we tracked neutrons produced only within this 2 meter, and this is the distributions of muons as a function of energy. We found that the muon induced neutron flux around 10 power minus 8 per centimeter square per second, This is again comparable to the flux estimated at Weep salt mine, which is at a similar depth, 1.6 times 10 power minus 8 per centimeter square per second. Okay. Then we calculated radiogenic neutrons. So, from alpine reactions, and spontaneous fission. So, the from alpine reactions, the distributions is shown here in this black. In the spontaneous fission, the energy of the neutrons produced from spontaneous fission is expected to be this red histogram. So, we take this distribution and sample around the experimental cavern in the rock, energy of the produced neutrons from alpine and spontaneous fission. We then calculate transmission probability as a function of rock thickness, similar as cosmogenic neutrons, and from that we determine the optimal thickness which we considered for tracking the radiogenic neutrons. Okay, so this is the transmission probability as a function of rock thickness. So, we see that above 1 meter of rock thickness, the transmission is less than 0.1%. So, this means we need not simulate neutrons produced beyond 1 meter. So, we considered 1 meter of rock and calculated the flux which reaches inside the cavern. This is the neutrons flux as a function of energy plotted here. It goes up to 8 MeV, and the total flux of radiogenic neutrons reaching the cavern above 100 kV, we found 1.12 times 10 power minus 5, and above 1 MeV, this is 5.75 times 10 power minus 6 per centimeter square per second. This is the total neutron flux shown in this, which goes like this. Radiogenic neutrons, it stops at 10 point minus 2 GeV, whereas cosmogenic neutrons, they could be energetic as large as 10 GeV. Yeah, and total neutron flux with energy above 1 MeV we found to be 5.76 times 10 power minus 6 per centimeter square per second. So, now we know the flux and how does it impact on the sensitivity of the of performing a dark matter search at JOSL is what I will discuss next. So, for that we considered some shielding which is typical in any dark matter search experiment. So, inside the cavern there we considered a layer of polypropylene and then lead and then another layer of polypropylene. I will come to the thickness of this in the next slide. And the detector is coated with Teflon and then copper. So, so we found that we then tracked again the cosmogenic and radiogenic neutrons produced in the rock through this shielding, and we found that a polypropylene layer of 40 centimeter stops almost all radiogenic neutrons, whereas it does not stop all neutrons from cosmogenic neutrons, because cosmogenic neutrons are more energetic than could be more energetic than radiogenic neutrons. So, we need to consider another layer of polyethylene of 20 centimeter after this, and in between the lead is considered to stop gammas which expected in dark matter search experiment. So, we found that only 10% of neutrons can transmit after this configuration. So, after this layers of shielding, the flux inside the cavern and that is incidenting on the detector we found to be 6.15 times 10 power minus 8 per centimeter square per second. So, there is some reduction of flux that is reaching the cavern after applying the shielding. Okay. So, with this we went on to calculate the sensitivity. So, in this left hand side plot, the expected the recoil energy distributions from neutron interaction is plotted we considered cesium iodide as a detector material and calculated limit on cross section as a function of dark matter mass. Here we only assume that the neutrons are the only background that is present in this experiment, whereas in reality there will be other backgrounds contributing to this. And we found the result, the cross section as a function of mass here shown in this blue curve, and compared to detector material, the same detector material cesium iodide in the Kim's experiment, this is shown in red. So, there is a very optimistic or very improved limit in here. This is because we only considered neutrons as the backgrounds. If we considered other backgrounds, this will go up. So, yeah, so with this, let me come to the summary. So, for the lift search analysis, we have now developed a GN4 based simulation framework to perform simulation for fractionally charged particles. This is now publicly available on Git. We are first to put limits below charge E by 3 times 10 power 6 and beta gamma range from 0.1 to 10 power 6. We calculate strongest limits for all charges below E by 120. The lowest limit of 1.36 times 10 power minus 7 per centimeter square per second per stray radian is achieved. In the neutron background simulations, we estimated neutron flux at the experimental cavern of Jadugara site. Flux above 1 MeV we found to be 5.76 times 10 power minus 6 centimeter per second. With this, when you calculate sensitivity to perform a dark matter search at JSL, we found that this is an experiment at Jadugara site could be feasible. Okay, this is all. Thank you.
Okay, thank you, Samir. Any questions to Samir? Okay, looks like no questions. So thank you, Samir. Let me just stop sharing. So now IPA has sent us the certificates to be given to the winners and the runners up, and we have the 2 winners and the 2 runners up. 3 of them are online, they are abroad, and Samir is here. So I would request Director IISER Mohali and my other colleagues in the committee, Professor Jim Libby and Professor Amal Dighe, to come over to the stage. We can. Dr. Anupam Ray, Dr. Subham Pandey, Dr. Biswajit Sahu and Dr. Samir Bani.
So now I request Professor Gauri Shankar, our director, to say few words about because he could not come during the session. He was very busy traveling. So I would request if he can say few words.
Good afternoon. It's a great pleasure. Although it's a very delayed welcome, it's still a very hearty welcome on behalf of IISER Mohali to all the participants in this year's DAE HEP Symposium. I'm delighted that IISER Mohali is hosting the Silver Jubilee event, which is the 25th symposium. And since this symposium is held once in 2 years, it actually represents 50 years from the year in which this program has started. And I'm extremely glad to know that the participation has been not only large but very enthusiastic, especially from students, mid-career and established researchers. I'm just a little sad for myself that I have not been able to be part of these gatherings for some reason or the other, both on personal visit and then on an official visit. I have had to be out of Mohali on Monday and Wednesday, Thursday. But I'm still happy that at least I could join all of you. As we are coming to the end of the scientific part of the program, and I understand that after lunch, it's a summarization as well as identification of the next venue for this conference. So once again, even at this late stage, my welcome to everyone, and I do hope that not only have you had a very fruitful scientific experience through the symposium, but also a very pleasant stay in this institute and in attending and meeting all your friends and colleagues. Thank you once again. Yeah, you can go for lunch.
Thank you very much. So now, before we end this session, I request Professor Rohini Godbole to say a few words about Professor Rahul Basu.
Okay, so all the Director Gauri Shankar, as well as somewhere there is an echo. Okay. As well as my friend Vedanta and all my all my friends on the committee who have been involved in today's deciding the awards which were declared today, and of course all my friends who have been awarded today the Best Thesis prize. First, I begin by wishing you all four all the very best and wishing that in future editions of this award, your students would get these. At least that is what I see and think would actually be something that would have made Rahul very proud, because Rahul, of course, was as Nilima already said, was a very friend of very long standing and a very close friend. He was a QCD expert. He worked on factorization in QCD as well as resummation ideas. In fact, we had only one paper together, but we had a paper on some calculations of higher order calculation of some higher order effects in forward jet production at ERA. And in fact, but apart from this physics collaboration, it was the person Rahul, himself was, physics was one part and a very dear part to him of physics that he did himself. But I think a very other important part of Rahul's personality was his responsibility towards community and the physics community. And in that sense, this award truly reflects his the time he spent on different activities that were of importance to the high energy physics community in general, beginning with the archives, which I don't know, all you guys, many of you guys are young, but you don't know that there was a mirror of of the LBL mirror of the archives, which used to be stationed at IISc, and that was the first one in India, the mirror site for the archives that was set up, and that was completely through Rahul's effort. And my own last memory of Rahul actually has been at the time 1 week we spent, I was visiting CERN, I think, for a longish time, and Rahul also came there for a while, and that was my last memory actually of Rahul, where we interacted together and as usual discussed physics, but equally well argued about where to go for dinner, where one does get good food. That was also part of Rahul's personality. So people knew him for his physics, but they also knew him for his mirror of the archives, and they also knew for the blog, which gave the list of very interesting restaurants in Chennai, and Rahul's suggestions never failed anybody. And also equally well, he was a great connoisseur of different types of music, great connoisseur of food, a great cook, and the most important thing that comes out of that I can remember of him was his breadth in almost everything that he did, and it actually also pervaded to the breadth in his physics interests, and that's why I think that Rahul would be very happy today seeing the breadth of the topics over which people have worked and people who have got the best thesis award, beginning from the work that Banik has done and Shubham has done, which indicates the kind of legwork that all our experimental physicist friends have to do for decades together before getting the one paper in PRL which says that we have found the Higgs boson, or some paper which hope someday we will get when we say we have found the dark matter. So I think this would please Rahul's, this would have pleased Rahul, and it would please his memory, wherever he is, very much. And once again, I actually want to also thank Nilima as well as Vedanga for giving me this opportunity, because I very much wanted to be part of this somewhat historic DAE symposium, and my health really didn't permit me to travel to Mohali. So I'm very happy that I got this chance to be part of these proceedings because of these few words that I have said. And I will again end by saying that as time is going by, the job of making a decision is becoming more and more difficult. In fact, I congratulate the 4 of you who have got the award, but I must tell you, and this is no reflection on you guys, for each one of you, who has got the award, we have had 2 more whom we could have equally well chosen, and there were some very fine distinctions and very fine arguments that we had to produce. So I would like to congratulate all those others who were also there, shortlisted in our discussions, and I congratulate them for having made our job very difficult. So this is wishing you all, the high energy physics community in India, all the very best in Rahul's memory, and thank you very much.
Thank you, Rohini. With this, we come to the end of the session. Again, congratulations to all the winners, and thank you for all joining. Thank you. Thank you for joining online, and we will send the certificates by post to you. Thank you. Bye.
Thank you.
Bye-bye.
Bye.
Thank you, Vedant. We'll chat later. So I have to leave now.
Thank you. Thank you, everyone. Bye.
Thank
Bye,
you.
Nilima.
Bye, Devashish. Yeah.
Bye.
Bye.
Hi, Rohini.
Thank you.
Very nice speech. I like it very much.
Okay, bye-bye everybody.
Bye.
And a happy new year in advance.
Happy New Year.
Not many days left of this year. Bye-bye.